Welcome to the XDC 2023, A Coruña, Spain. Thank you for coming. I hope you enjoyed the welcoming event yesterday evening. I'm happy to see you here. I know that it was great. I would like to do the housekeeping at the beginning of this opening session. I'm Samuel Iglesias, by the way, member of the organization team of this conference. So I would like to thank the sponsors of this conference, starting with the platinum sponsor, Igalia. Igalia generously organized this conference here in A Coruña, Spain, where we have our headquarters, and we are sponsoring this conference as platinum sponsor, among other things as I will explain later. So thank you, Igalia, for this support for this conference. I would like to say thank you as well to the gold sponsors that we have at XDC, starting with Google. Thank you so much for your contribution to this conference. Similarly, I would like to say thank you to Collabora. You are also a great sponsor, always there when we need it. I would like also to say thank you to ARM. You are also a great sponsor, and we are proud to have you here as well in the roster of gold sponsors. And finally, Microsoft, that all of you know already. So thank you, Microsoft, for sponsoring XDC. Then we have the silver sponsors. We'd like to start with FexEmu. Thank you so much. You were actually the first one sponsoring the conference, so thank you so much for your contributions. I would like to thank also the Linux Foundation for all their support, AMD and Qualcomm, because you are here listed as sponsors, and we really, really appreciate you and your contributions to open source as well. Then the bronze sponsors, we have the Kronos Group and Codeweavers. Thank you so much for contributing to this conference and to make it happen. And finally, we have a couple of supporters, Turing's office in A Coruña, that will sponsor, as you will see there later, an event in the afternoon, and the local user group called Gpool, who is helping us in the organization. We are having volunteers from this local Linux user group, and they are always helping in all the events that we organize here in A Coruña. Thank you so much. The welcoming event that you have been yesterday evening, it was sponsored by Igalia. Thank you so much. I hope you enjoyed. I hope you enjoyed the Galician bagpipers. And also the food, the drinks, and the most important things, the people. Because actually this is the idea of this event is to, the halfway track, which is actually the key component of this conference. The coffee breaks are sponsored by the X.Org Foundation. Thank you so much. Coffee breaks. Coffee is the most important thing of a conference after the Wi-Fi. So thank you so much for sponsoring the coffee breaks. And finally, as Igalia is sponsoring the lunches, you are going to have the lunch in the same place that we had this welcoming event. And similarly with the coffee breaks, they are going to be on the other side of this floor. And they are going to be sponsored by Igalia. So as we have 1 hour for lunch, it will be great that you don't need to go outside thanks to Igalia. Then some important info. The main room is this room. So you are here, you know where it is. And for the workshop room, it's in the other side of this floor, next to the coffee break and lunch area. But to get there, it's not possible to do it through the lunch and coffee break area, but you need to go at the end of this corridor and turn left. It's going to be at the end of it, so in the other corner, actually, from where I am standing. Wi-Fi, again, the most important thing of a conference. The Wi-Fi is here. You have your QR code. There are signs everywhere. very important thing here is that the free desktop community, we are very proud of being so welcoming and inclusive. So, and that is reflected in our code of conduct. As you are registered attendees here, you accepted this code of conduct. Just in case, you have a link if you want to read it, and if you need to report any breach, you have a list of code of conduct committee members here listed, and a phone number in case you would like to talk to us directly. Here, this is the QR code of the program for today. But I think it's best if I can explain you that we are going to start just in a moment with the HDR talks. Then they are continuing with Nouveau MVK. We have a break of half an hour. Remember that this break is going to be happening in the other side, where the welcoming event was yesterday. And followed by writing compilers and the analyze the graphics magic with Alyssa and Lina. And then we will have the lunch from 1 to 2 p.m. And about the workshop, the only workshop that we are having today is going to start just after lunch. So remember, to go for the workshop room, you need to do the U thing to get there. And then we continue at 2 o'clock the rest of the talks until more or less 6 p.m. where we finish. Once this is finished, we are going to do the social event today, which is a guided tour sponsored by the touring office of Coruña. There are going to be several guides talking in English, so don't worry about that. And they are going to give you an explanation of the city center of A Coruña. It's going to start at 6:15 in front of this venue, and the duration more or less is going to be 1 hour and a half. It's going to end in Maria Pita Square, so it's quite convenient if you would like to have lunch, to have dinner just afterwards, because this area has a lot of restaurants around, so it's going to be easier for you to spot a place to have dinner. For more information, announcements, or you have questions to speakers, especially if you are attending remotely, we have a matrix room. You can connect using this link. It's also available in the website. And to following news, we have our own Mastodon account that you can follow as well for the latest and greatest announcements and posts. And that's it. Enjoy the conference. Thank you so much. Okay, HDMI cable.
Can you hear me? Okay, yeah. So, hi. Hi! I am Alyssa from Igalia, and welcome to the Rainbow Treasure Map, a talk about advanced color management on Linux with AMD Steam Deck. So first, if you are not used to the topic, you may find some useful links in this list. And when we talk about colors in the graphics chain, we should keep in mind that we have a wide variety of source content colorimetry, a variety of output display device, and also internal processing. And then users expect consistent color representation across all these devices. So to get it, the user space can use GPU-accelerated color management. However, this requires an interface with the display kernel drivers that is currently missing from the DRM KMS framework. So since April, I have been bothering, the DRM community by sending email patch sets with more than 30 patches from the work of Joshua and me to add driver-specific color properties to the AMD display driver. Meanwhile, discussions on defining a generic color management interface are still ongoing in the community, and we are still not clear about the diversity of color capabilities among hardware vendors. To bridge this gap, we have defined a color pipeline for Gamescope that fits the latest versions of AMD hardware. It delivers advanced color management features for gamut mapping, ADR rendering, SDR on HDR, and HDR on SDR. So AMD frequently releases new GPU and APU generations, and each generation comes with a new DCN version with display hardware improvements. For this work, we use AMD Steam Deck hardware and its kernel driver as a reference. The Steam Deck is an APU with DCN301 display driver. It's part of the DCN3 family. And knowing this is important because newer AMD DCN drivers inherit implementations from previous families. Additionally, each generation of AMD hardware may introduce new color capabilities. So it's important to familiarize yourself with your specific hardware. The AMD driver in the Linux kernel space consists of 3 layers. The first, top and down. The first, the DRM KMS framework, then the AMD Display Manager, the DM, and the AMD Display Core, DC. So we extended the color interface exposed to the user space by leveraging existing DRM resource and connecting them with the driver-specific functions for managed color properties. So to connect DC color capabilities and the DRM API, we needed to do a significant transformation of the color management functions and helpers in the AMD Display Manager. AMD Display Manager is the Linux-dependent part of the driver that connects the AMD DC interface to the DRM KMS framework. It's intermediates communication too. So, and the AMD DC is the OS agnostic layer. So examining its code that is shared between platforms, different platforms, and different DC versions help us understand the AMD color pipeline and hardware capabilities. Since the machinery for hardware settings and resource management are already implemented there, or yeah, most of that. So now we arrived, I started to talk about AMD DC, and so let's take a look at the AMD Display Core Next, the newest architecture for AMD display hardware. Here we have 2 blocks. that have the capability to manage colors. The display pipe and plane, DPP, for pre-blending color adjustment, and the multiple pipe and plane combine for post-blending color transformations. So now let's see what we have pre-blending in the DRM API. This is what we have for color management before blending. Okay, it's, I can say nothing, but it's not completely true because we have color encoding and color range properties for the input color space conversion. But both input and output color space conversion are already linked to the generic, the KUnit generic API, and it's not part of this driver-specific work. So in case you are not familiar with the AMD shared code, I am not an AMD expert either, but I talked about it in the last XDC. In short, we need to draw a map, link points, and navigate there. You can see that we have some post-blending color properties on DRM, but there is nothing before blending yet. But thanks to the shared code, much of the hardware programming for AMD was already implemented in the DC layer. You can see that below. So, and it's not only the properties that was missing, but also the connections to the DC interface. So that's when our search begins. Looking at the color capabilities of the hardware, we arrive to this, okay, here. Oh, where is it? Oh, sorry, not so good. Okay, we arrive at this set of color properties. I can say that it was not that like that because we built this pipeline and discovered our needs throughout each iteration. But okay, the first property was the plane D gamma. It was our first driver-specific properties before blending. It's used to linearize the color space from encoded values to light linear values. Here we can use a predefined transfer function and also user lookup table. I will call TF and LUT from now. So predefined transfer function are for this block is a hard-coded cube that go to the D gamma ROM block, and this is the list of the transfer function that the drive support for this block. So we also have one-dimensional LUT that has the usual size of 1D LUT in the DRM's subsystem. That is the 4096. And it's an array of DRM color LUT elements that goes to a different block in the hardware, the DPP gamma correction block. Then, finally, we have our first path unlocked. And now we will introduce the next one, the color transformation matrix, CTM, for color space conversions. Yeah, the link. So it's a 3x5 fixed point matrix that goes to the DPP gamut remap. It's another block. And, but here, we need to pay attention that there was a trap here because both post-blending and pre-blending were going to the same block, the pre-blending gamut remap. So we needed to work here to detach this CRTC CTM from there, I think. Yeah, that from there to the right way. Yeah, so now each CTMs go to the right path, yeah. And we have another path unlocked. Next, the ADR multiplier. It's a factor applied to the color values of an image to increase their overall brightness. Yeah, it's useful for converting images from standard dynamic range to a high dynamic range, ADR. And it can range beyond 0 and 1, so subsequent transforms need to use PQ transfer functions. Then we need a 3D LUT. But 3D LUT has a limited number of entries in each dimension, and we want to use it because of it, we want to use it in a color space that is optimized for human vision. That means in a nonlinear space. Therefore, user space need one 1D LUT before 3D LUT to linearize content before apply the 3D LUT, and then another one after that to linearize content for blending. Yeah. Oh, yeah. And then this first, the pre-3D LUT Pre-3D LUT curve is the shaper curve. Here we enable two properties, one for predefined transfer function and another for one-dimensional LUT. But here there is no hard-coded curve. What we do is AMD has a color module that is capable to calculate the predefined curve from predefined coefficients. And this is the list of supported curves. So what it does, as we have TF and LUT values, the color module combines both and into one LUT that goes to the DPP shaper RAM block. And 3D LUT is our rockstar. 3D LUT is perfect for complex color transformations and adjustment between color channels. It's also more complex for manage and require more computational resource. So that's why the number of entries is limited. So an array and a 3D LUT contains samples from the approximated curve, and values between samples are estimated by tetrahedral interpolation in AMD. AMD support 17 and 9 as the size of a single dimension. And the blue is the outermost dimension and red innermost. Then we also need, as I told you, a post-3D LUT curve to linearize content, the color space before blending. This is done by the blend TF and LUT properties. It works similar to shaper LUT, that there are no harded curves for blending predefined transfer function. And the curves supported here are the same of the D gamma block that is calculated by the color module. The resulting LUT goes to the DPP blending gamma block. So we have our pre-blending properties connected. Okay, there was a conflict. If you see, there is a conflict between the DRM CRTC D gamma and the DRM plane D gamma, and it is inevitable. And our approach now is not accepting that both are set at the same time. We also optimized the color, the conversion of the frame buffer to wire encoding by adding support to predefined CRTC gamma, the gamma TF, the last one you can see. It operates similar to the shaper TF, no harded coded curve, and the TF and LUT values combined by the AMD color module, and the resulting LUT goes to the MPC gamma RAM block. So this is the AMD driver-specific color management pipeline on Linux, and armed with this comprehensive knowledge, you are now ready to enjoy the rainbow treasure of AMD display hardware. And yeah, conquer the world of graphics and visual computing. In this work, we have now the Gamescope Steam Deck embrace the color capabilities of the AMD GPU. And you can see in a high level, oh, the image is not so good, but yeah, it's just describing how we map the Gamescope color pipeline with each block, color block on AMD. And okay, my time is not okay, but okay. So DRM subsystem contain not only this treasure map, but many other hidden treasures from different vendors. And that means that the search for the rainbow treasure is not over. We want more complex transformation and adjustment available in Linux, and we want to expose all GPU capabilities from all hardware vendors to the Linux user space. Finally, I would like to thank Joshua and Harry for all the fun in this collaborative work. Also, I can say we made it together. And also Rodrigo Siqueira and other AMD display developers for the availability and all the feedback that they provided. Everyone in the DRI community who contributed to this adventure. And yeah, the amazing part of this, the power and impressive part of this work is not here, comes next with Joshua and the Rainbow Frogs. So yeah, is it. Thank you, and questions? Okay, sorry, questions? Someone want to ask something? Okay, you can ask Joshua. Next, not me, sorry. Nobody is raising hands, yeah. Hands. Okay, one more. There.
Is it working? Yeah, is it working? So the question is the following. If I remember correctly, this uses the proprietary properties. I mean, this work, isn't it?
You mean how to use it?
No, I mean that your work uses driver-specific properties, not the generic.
Yeah.
Yeah, okay. Do you plan to make them available to other drivers? In some way, I saw the concurrent proposal. What is the plan for the convergence between?
Oh, I see.
Yes.
Yeah, this is like our short-term proposal to have something to start to understand what we have available in the system, in the subsystem. But our long-term plan is to adopt this in a generic API, in the generic interface. It will be easier for AMD because we already mapped everything. It's just a matter of switch to a different interface. But the programming setup and resource management are done. So, but our long-term plan is to adhere the generic interface. Yeah.
Which user mode did you validate this with?
I didn't get.
Which user mode did you validate this pipeline with?
Which user mode?
Yes.
You mean user mode driver?
Yes.
But in the KMass we use a generic interface. It's not by user mode driver. I mean, it's not like Mesa. Is that thing?
Do you mean which composer?
Yes. Yeah. I meant which composer?
Oh, the Gamescope.
Okay, so the Gamescope is plugged in with AMD specific properties, and that's how you validate.
Yeah, Gamescope use the driver specific properties right now.
Thank you.
It's the next presentation. We'll clarify you about how it works.
have a question from the Matrix. What is the situation with upstreaming the vendor-specific properties? We usually don't allow driver-specific properties nowadays.
Yeah, it's still in place, I can say like that, but what we are doing is to use a guard for these properties, at least for who is interested in experiment and start to be more familiar with the properties, can already play with that. And we are in the 4th version. I think it's maybe the last one, and it will be in the upstream sooner, I think so. Because the generic API, as I said, is discussion is still ongoing. So we will need more time to define it. Yeah. Time is over. Thank you. Bye.
So welcome to my talk, Rainbow Frogs, HDR and Color Management in Gamescope. This is going to cover all of the different things that we've done in Gamescope for color management and HDR on Steam Deck in like the past year or so. But unfortunately, this talk is abridged because I wrote a lot of slides and I then realized I only had 20 minutes. So we're just going to power through them. Hi, I'm Josh. Hello, everyone. Thank you so much. I work on Gamescope and Steam Deck and DXVK and Mesa for Valve, and yeah. So some people here might not know what Gamescope is. Let me explain. Gamescope is a Wayland compositor for gaming used on the Steam Deck with very low latency and targeting very low power consumption. And really, Gamescope does everything. We have HDR, color management, display timing, VRR, low latency. We do blending in all the right spaces and everything. And, but most importantly, now it includes color management, which is really cool. So why would we want color management on the Steam Deck? Like, that seems like not something gamers would care about, but really we do, because the internal display of the Steam Deck has a fairly modest gamut of only like 82% sRGB, but consumers really want a much more vibrant display. So one approach that we could use to do some form of gamut mapping is the existing CTM matrix in DRM, but the problem with that is it introduces really horrible clipping. It does make it a lot more vibrant, but people really know something's off. If you AMD Display Core is really cool, and if you watched Melissa's talk that was just before mine, you would know that. And so there's lots and lots of features, but the most important one there is that we have a shaper and a 3D LUT, which means that we can do like film grade tier, like color management, and yeah, all of that. So we have much greater control. We use a CTM near the gray axis and just smoothly decrease the influence as we get closer and closer to the gamut edges. And yeah, it looks a lot better. There's no clipping. If you download the slides and look at the image before and the image after, you'll see it looks a lot different. But it's pretty hard on a projector to really show it off there. Yeah, so how we expose this in the UI, not everybody, like we're changing the default behavior of the vibrancy of the Steam Deck, which is not everyone's going to want that. Some people might want more than what we want. So we added a UI where it's just a basic vibrance slider which controls the gamut wideness for SDR. We don't actually increase the gamut wideness for any HDR content. That's always rendered completely faithfully. And we also added color temperature because a lot of people on Reddit started to ask for it. And yeah, rolled in night mode and everything like that. So another question is HDR. Now, if you see on the screen, there's an image of a HDR TV, and yeah, lots of consumers are really interested in HDR and gaming in HDR, so we want that on the Steam Deck. But HDR is hard. Harry Wendland did a talk last year, and there's lots and lots of nuances to go through, but knowing what we know about the AMD display pipeline now, HDR is not that hard for us. So what's traditionally hard about HDR? Well, there's lots of little things that you have to get right. You can have mixed HDR and SDR monitors, mixed HDR and SDR windows even on deck for like drop downs. We have like the quick access menu. We have like the Steam overlay. So we do have to handle mixed HDR and SDR content. There's a multitude of HDR formats like PQ, sCRGB, which is just pretty similar, absolute as well, linear and nits over 80. You have to have all of your internal color processing over 8 bits per channel, otherwise you just start to get horrible banding, especially with PQ, where on a lot of displays you're kind of throwing away the high end because, yeah, like if your display is only like 500 or 1000 nit, like a large part of that range is just completely unused. You have to parse and patch EDIDs because, yeah, you need to have some way of funneling all of the display metadata about the maximum luminance and the minimum luminance of the application. And all of our HDR content is Win32. And Wine only supports X11 right now. Gamescope is very X11-centric. We have to support undocking for HDR games so users can get out of the HDR experience or at least play it in like a decent-ish way. And supporting HDR throughout the whole stack is just really, really hard and a lot of work because we have to funnel everything through. There's like DXVK, there's VKD3D Proton, and yeah. So despite showing a single window, we have mixed blended content. We've got the performance overlay, we've got the quick access menu, we've got the Steam overlay, we've got drop-downs and modals that can appear. Our solution for that is to simply just use the existing color pipeline and use a shaper transfer function to go from gamma 22 to PQ, and then we use the blend LUT on that is per plane to go to linearized display referred space, and then we re-gamma that back up to PQ, and everything's blended fine, and it just works after a lot of work dealing with the precision issues in the kernel pipeline, but it works now. We also have to handle sCRGB, which I alluded to before. There's lots of sCRGB Windows content, such as Cyberpunk 2077, and the problem with sCRGB is it relies on negative values to represent values outside of the 709 gamut. And the easiest solution to that would be to just do a color transform matrix from 709 to 2020. And that's exactly what we do. Some people in the audience might be thinking, oh, you should use the HDR metadata. It gives you all the primary info. But then you have to trust that the app is not completely stupid and giving you completely wrong information there. The HDR metadata is very unreliable. It's very rare that apps actually set it correctly. Quite often, you'll get values where the primaries are all 0, the primaries are always 709, even though it really wants more out of it, or the max luminance is something like 200,000 nits. You just can't trust it. So we just do a color transform matrix from 709 to 2020, and then we're already in the space to go straight to PQ. With the shaper transfer function, and then we use the exact same color processing pipeline that we use for the rest of HDR. So another problem is that we need our scan-out to look completely identical to when we're doing composition. So we had to implement tetrahedral 3D LUT interpolation, so I converted the code from OpenColor.io to a shader that just uses a 3D texture. And another problem is that the D-gamma ROM on AMD GPU, only for the ROM, not the LUT, is applied per tap. So that means that if you're doing bilinear and upscaling, that means that it's being upscaled in linear space and then going blended back. So we have to do that as well. And Vulkan and OpenGL, etc., doesn't have something like a PQ image view, so we don't automatically get that linearization there. So we have to implement bilinear ourselves manually in the shader for HDR to do texture gather for 4 texels, do the D-gamma, then blend them together with the weights. This is important as most people on the Steam Deck will be using 720p, 800p scaled up to some insanely large TV size like 4K, so it's important to get this right. And blending in PQ space looks much worse than blending in sRGB. So doing the end-to-end part of HDR was a lot. Like I did a bunch of experiments with KHR display. I did a bunch of work so we can get the 2020 on the output because the color space property in the kernel was broken, which is very fun. Yay! And we did all the kernel stuff with Melissa. Thank you. I really appreciate it. We had to get the display in HDR mode, which was, well, I didn't know anything about HDR when I started this, so it was quite the interesting minefield, especially when what do you set for, like, if you're displaying SDR content? One of the main problems there is if you set the max display luminance to the same as like the full frame luminance, then some displays will look completely fine because they don't care. They don't do tone mapping themselves. They just clip. But some TVs will just take that and be like, oh, your full frame luminance is going to be the same as your max mastering luminance? I'm going to just tone map the hell out of you. And it looks completely broken. So for SDR content, we just have the max and the full frame luminance set to the max full frame luminance in the EDID so the displays don't break themselves. We also need some way to read the EDID and DXVK. Thank you, Simon, for libdisplayinfo. I really appreciate it. It's really cool. Please make it work on Windows. I had to port it to DXVK because we also have to read the EDID there, which is really fun. Gamescope just passes the EDID to the application using a root window property, which is a horrible hack, but it works. We also patched the EDID to hide the Steam Deck's rotation, so it gave me a good excuse to finally go ahead and do it. So we do all of that. We had to do it on the swap chain side. That's what the different HDR color spaces in Vulkan, map to. We followed the HDR metadata, but unfortunately, as I mentioned before, the HDR metadata is hopelessly unreliable, and that's probably why a lot of games look really bad when they're setting 20,000 nits as their mastering luminance and they're not getting filtered out. Luckily, we filter out bad HDR metadata in Gamescope right now, but it's still in the air whether we should actually send it to display at all. We had to support NVAPI and AGS, which really sucked because they just override the whole screen. They don't do anything per surface or per swap chain. So yeah, that's just a whole thing, which makes SDR content look bad. My implementation of that just sets like some global state, and DXVK then sets every one of its swap chains to have that color space. And it works. Phew, I'm glad that's over. But Josh, how can we support HDR when Gamescope only supports X11 clients? And my answer to that is I don't know. Thank you for coming to my talk. Goodbye. No. We have the Gamescope WSI layer. And the Gamescope WSI layer just takes a... it's a Vulkan layer that when you create a Vulkan swap chain, it creates a Wayland surface underneath and then says to Gamescope, hey, this X11 window right here, why don't you just replace it with this Wayland surface? And then we just use the Wayland WSI, and we do a lot of back channel stuff. And there's a lot of advantages to it as well. We get lower latency. We're not limited by visual ID, so we can get 10-bit through and through with scan-out dithering on AMD GPU, which is great. And we can implement and iterate on anything we want without going through X-Server, Wayland protocols, Mesa, and we also implement display timing. It's a flawless plan aside from child windows. They're horrible. So what we do there is we still have to fall back to X11 sometimes, but it's only if we have a child window that's not covering the entirety of its parent, or it's a top-level window with a child window that isn't. So we have to do a lot of magic to unpick that because there's the two things. So yeah, it's not a compliant solution, but it's good enough. If we transition to being able to bypass to not, we just send out of date to the app for it to remake its swap chain. And if we can start to like transition to use a Wayland swap chain because the child window started to cover it or whatever, we just send suboptimal so it will remake it when it's ready. So now what? Upstream Wayland color management is still pretty in its infancy. There's lots of debate about it. It's 4 years old. There's no Mesa implementation at all. And so widgets are our own thing. We have a custom protocol for Gamescope to talk to the compositor. It implements the X11 window replacement with override window content, originally made by Simon, but I had to fix a lot of bugs with it. The simplest thing ever. It just sends the VK color space KHR over the Wayland wire, and, well, we could do better. We could have a protocol enum, but we don't have a need for it right now. We'd send the HDR metadata over the wire in the exact same way you'd send it to a HDMI or DisplayPort sync over the wire with CTA 861.G format, which is basically just the exact same data you have in Vulkan as floats, but just mapped to some fixed point mumbo-jumbo. Yeah, there's the link if you want to check it out. So that's like the main color pipeline. And as you can see, for sRGB, there's no degamma. We just go to 709 to 2020. We go straight through the shaper to put it in PQ. We do all the 3D LUT stuff that we normally do, and then we just blend it back, same as everything. And then for HDR10, we just don't do the color transform matrix, and we still have the degamma that's per tap. And then for SDR and HDR, we just do we have a degamma of sRGB to linear, but then we have the shaper transfer function actually go from gamma 2.2 to PQ with like our HDR brightness scale and the night mode and all of our SDR gamut wideness for HDR as well. Yeah, then that just gets blended as well. Future kernel work, things that we need. We need 3x4 CTMs. Please, I beg you, we need 3x4 CTMs. I can't tell you why yet, but eventually you'll see. We also would like to split up enabling and setting of the lookup tables, because setting a big 3D LUT on an atomic commit with all the register rights is a lot of work, and it takes multiple, like 8 milliseconds or something to set a full 3D LUT, which takes forever, which means that you can miss vsync, which sucks. This is what it looks like right now. It's really slow. Yeah, so that's our future work. We have a bunch of cool tools. We have a full HDR analysis suite by Lilium available in developer options right now. We have heat maps for debugging. If you're interested in HDR and you want to see how it actually works, please use these tools. If you're a game developer, please use these tools. I promise you they will help you out. Here's some pretty pictures. There's the HDR analysis suite running in Gamescope. There's some cool heat maps. It kind of looks broken because the projector has a very poor black level. But yeah, you can see like all of this is like 400 nit to like 1,000-ish. Yeah, so it's all the way coming through. This game is Armored Core 6. Thank you for coming. Any questions? And special thanks to Harry, Melissa, Jeremy, and Lilium. Sorry about it being so quick, by the way. I only had 20 minutes.
Not really a question, just saying that your Wayland X11 hack is impressive and terrible, and I kind of love it.
Yeah. So far, we haven't had any problems with it, which surprises even me. But yeah, we've shipped it to users now, and so far we haven't had any problems. And we're hoping to also enable it for not just HDR games, but like every game, because the majority of games these days output 10 bits per channel, like UE4, UE5, basically every modern game engine outputs 10-bit, and we would really like scan-out dithering, because it really helps with banning.
Hi, we have a question from Matrix. Dodo GTA asks, how hard would it be to make Gamescope properly work with the experimental Wine Wayland driver?
We have very, very basic support for XDG shell right now. The problem is, right now, we don't get enough information. And so one hack that we have in Proton is that Wine will literally send us the Win32 window flags as a property on the X11 window. And we use that for a lot of determination of like focus and all of that sort of thing. So we need a way to like get all of those focus hints. Like Gamescope is a very gamified console-like experience, and we need to keep that at like feature parity before we start moving to Wayland and stuff like that. But it would be like nice someday, but right now the swap chain override stuff is servicing us better than doing all of the work to make sure that focus and everything in Gamescope with Wine Wayland would work properly.
Hi. So there's now a color management protocol, which is, I think, mostly done with the bike shedding. Is there any plans for Valve to implement or to help with the implementations at least? Because I think that's one of the things they're still struggling with, which is having an implementation where they can find all the necessary bugs that might still be in a protocol or in the spec.
We're happy to like help test stuff out there, but doing the whole implementation when nobody has really done a Mesa branch or anything yet, it's not really worthwhile for us right now. Like, I don't think adding a Mesa branch to like all of that stuff is like particularly difficult, but it's also not super needed, and well, at least for us right now. Any more questions? Okay, thank you.
Hello? Hello? Hi. Hello? Hi, everybody. My name is Faith Ekstrand, and we've got Karol Herbst over here, and we're going to be giving a quick update about Nouveau and NVK. Hopefully this is a little bit more interesting, has a little more content than maybe your average State of the Nouveau talk that we've heard over the years. We've been doing a lot of cool stuff, and we're really excited to sort of share what's been going on. Quick overall overview, we've got some kernel stuff that's been happening, new AU API, GSP firmware, hardware support, we've got a bunch of user space stuff that's been happening, and we're going to try and go through all of it today. All right, so we'll start off with the kernel. One of the things that we had to do in order to get NVK up and going is we need a completely new user space API. Vulkan presents a different set of challenges than OpenGL, and the old API was not really up for the challenge. One of the things we needed arbitrary sized command buffers, whereas the API had a hard limit of, I think, 512 push buffs or something like that. We also needed an arbitrary number of BOs in a single submission, and the old one had a hard limit of like a couple hundred. I don't know why we even tried to claim that we had OpenGL with bindless, because we really didn't. We needed to be able to handle memory aliasing of tiled images. That was not possible thanks to NVIDIA's lovely usage of putting the tile mode in the page table entries, which meant the tile mode had to go on the buffer, which does not work for Vulkan. We wanted sparse resources. We wanted explicit synchronization, which had not been hooked into the new API. Lots of stuff was missing. So basically, we tossed the whole API and created a new one. The new API is based off of, one of the cores of it is this vmbind diactyl. Vmbind allows you to take a range of a buffer and apply it to a memory address. And we use that for everything. Gone is the create a buffer and get an address back. We just give it the addresses. Sparse binding is fully supported, so we have page aliasing with multiple pages, with the same page going to multiple VAs. We have sparse null pages for soft faults in texturing. We can bind things either immediately, or we have a pipeline system where we provide a set of sync objects in and out. It gives us everything, so it gives us everything we need for sparse. And the big thing that it gives us, which made Vulkan even possible, is the tile mode and the PTE kind are set at vmbind time and not at BO creation time, which means now we can have multiple depth buffers with different formats overlapping each other, like the Vulkan spec requires us to be able to support. So yeah, it gives us what we need for Vulkan. It gives us, yeah. New exec diactyl, it's much, much simpler than the old one. Gone is the BO list. It just assumes that everything is VM bound, and that's it. When you have, we also added a flag. I didn't really talk about that in the slide, but there's a flag on BO create that says whether the BO is exportable or not. And for non-exportable BOs, we now have a single DMA reservation object for all of them. And so we don't have to walk lists of buffers and lock them. Instead, we just take one lock and move on, which makes submit way faster. The actyl itself just takes a list of addresses and lengths. It doesn't actually need to care about what buffers are there because they're already bound, and we just fire them off. And it's now 100% explicit synchronization. So no more implicit sync on BOs, no more hacks inside Vulkan where we have sync objects that are backed by BOs. That was awesome. And everything is now DRM sync object. So yeah, all the implicit synchronization stuff is gone. If we want to do implicit synchronization for something like Windows System integration, we have the DMA buff import export sync file actyls that I added 2 years ago, 1 year ago, I don't remember, which mean that we get real, from Vulkan's perspective, we get real explicit synchronization, and from the perspective of the Wayland compositor that's running in Glass, we get implicit sync, and everybody is happy. And we also have timeline sync objects from the beginning. So we get timeline semaphores and import, export, all the good things. So there's the new kernel API, and I will hand it off to Karol, and he's going to talk about GSP and a few other things.
Test. Oh, okay, already working. So NVIDIA, I think it's already a year or more ago, released the so-called GSP firmware inside with their open source driver, and that's something we will use in Nouveau as well. It gives us reclocking, all the good things we are missed out in the past. And there are already some patches merged for this. We had needed a quite bit of display related to work, which is already merged. And we have a couple of tested on the mailing list, which are getting worked through and merged as soon as possible. The annoying thing about this firmware is it's 25 megabyte big per file. And we need them, currently we need 2 of them. And because we have to ship old version of this firmware file and new version because of kernel rules and everything, and we will support more generation going forward, this will explode. This will be a huge problem for distributions if they don't change the way they are handling firmware files. Currently, for example, Fedora has 3 kernels installed with 3 init RAMFS files. So we already have 150 megabytes just wasted on the firmware files. If your boot partition is 1 gigabyte big, you can run out of space soon. So to tackle this, Dave came up with an idea. It's somewhere on the mailing list. It's quite old, but it's basically an idea to version group of firmware files so that user space can say, okay, I have this 100 files, but I actually only need 10 of them because the kernel already supports the newest ones. So that's one way to get rid of all the old firmware files we don't need anymore. And hopefully this will be enough. But maybe the firmware file is getting bigger. Maybe we have to, or distributions have to figure out a way to not include firmware files into init RAMFS, because I think this is a problem which has to be solved one way or the other in the future anyway. But what's actually good about the firmware files is that it's the first time we actually use the same firmware files NVIDIA is using. Before, with all the going with Maxwell 2, NVIDIA gave us special firmware files which were different than the ones they were using, so we couldn't just use theirs to get new hardware support. But in the future, by just using the same ones, we can enable hardware much quicker and don't have to wait for NVIDIA to give us the firmware files we need. Yes, and this kind of gets us to Ada support and kind of also Ampere. Ada will require GSP because NVIDIA won't give us the old style firmware files we used in the past. So yeah, Ada support has to wait a little more until all those patches are merged and the distribution figured out their firmware stuff. OpenGL support is merged for MP in 23 and for Ada in 23.2. I've tested it locally with GSP. You can't test it, but it's in Mesa, so you just have to wait. And it also should just work in NVK once that's there. NVIDIA also released Hopper as a GPU. Sadly, nobody has been able to actually test if the Nouveau code is working with it because the hardware is expensive and nobody really has it. If somebody of you has it, please give it a try. We know that the compute support is a little bit different and the GPU support is also kind of weird, but I think from a hardware perspective, it works the same. It's just very slow. So there also have been a couple of OpenGL improvements. I fixed multi-threaded OpenGL, which a lot of users are hitting now, and I think they are actually using fixed Mesa version by now. So if your Slack application doesn't crash anymore, it's because of this. And other Electron applications. Chromium actually added a workaround for Nouveau, so they didn't hit it, but all the Electron applications didn't apply this workaround. So if those crashed for you in the past, it should be fixed now. And I've also managed, and others as well, managed to fix NV30, which is like, I think, 20 years old hardware or something. But it has been broken since forever. And there was some really weird bug, and if you started GNOME with it, it's just random garbage rendered on the screen. But it should work now. So in case you have an old GPU, it should work. So yeah, let's talk about NVK.
All right. So we've been working pretty hard on NVK over the last year. And everything I'm going to talk about has just happened since XDC last year. So first thing is that we've implemented a few features. I apologize for the font size, but I had to get it all into one slide. There are 62 extensions and feature names on there that are interesting. I will point out a few of them that are of particular interest to people. First is geometry and tessellation shaders. We did not have those hooked up. The compiler work was basically already done because at the time we were using the old Nouveau compiler, but we hadn't actually done the work in the pipeline to get stuff hooked up into the compile process. Those are up and they work now. I had a GSoC intern over the summer who did YCBCR, which was not especially interesting to a lot of people, but it is one of the big Vulkan 1.1 features, and it had a pretty big impact on the driver itself because it involves multiplane images, and for anybody who's worked on a Vulkan driver, those kind of end up all over everywhere, and so that was a big refactor that happened. We have a bunch of the extensions that are needed for DXVK. We've got like the depth clip control, depth clip enable. We've got all of the maintenance extensions. We've got all of the extended dynamic state extensions. So all those good toys. Joshi was bugging me yesterday about depth bias control, and I am working on it, but I don't quite know how the hardware works yet, so we're still figuring that out. But we've got a lot of what's needed. I don't know that we have everything for DXK quite yet, but we do have some apps that are up and running. We have somebody on our channel who's been playing with DXVK successfully for close to a year now. But I haven't been out specifically testing games. I've been focusing on trying to get CTS tests passing. But yeah, we've got most of what's needed. We should also have most of what's needed for GL 4.6 on Zink, as well as lots of various app things. Again, not incredibly well tested, but theoretically we have most of the features. We also merged into Mesa Main. So that happened, what does this say, 2 months ago? We landed in Mesa Main. It's all hidden behind the Nouveau experimental enable. And it's going to be called experimental for probably a little while yet, because even though we're in pretty good shape these days, we're still working on filling in a lot of stuff, and it hasn't gotten broad testing, but lots of stuff is working. Currently, we are supporting Turing and later GPUs. We're hoping to backport that back to Maxwell and maybe even Kepler. Currently, everything Kepler and later will enumerate if you enable the I want a broken Vulkan driver flag. And if you enable the I want a broken Vulkan driver flag, you get what you asked for. So please be aware of that. But yeah, everything back to Kepler should enumerate. Maxwell works pretty well, at least Maxwell B. I have not really done anything on Kepler, so it's probably a dumpster fire, but in theory it will enumerate. We require a Linux 6.6 kernel. This is because that's where the new UAPI is going to land. So the new UAPI is basically required for properly implementing Vulkan, so we are not supporting the old one. We had code for a while when we were originally bringing up the driver, but that code has since been deleted. It is gone, it is dead, it is never coming back. You need a 6.6 kernel, or you can grab DRM-esque fixes. That also has everything in it. And yeah, we're not going to do the old one. Currently, as I said, it fails 4 CTS tests. That's not true. It fails 0 CTS tests. We'll get back to that. The last year, if you've been watching the main NVK repository and wondering why things have been a little bit quiet, it's because I have not been working on NVK primarily. I've been writing a new compiler. The user space stack is getting a complete top-to-bottom refresh. And part of that means new compiler. Among other things, the new compiler can actually reliably allocate registers, which is good. That's always been a bit of a problem. So yeah, it is a completely brand new code base. It's being written in Rust. the next talk is going to be about my experience writing a compiler in Rust and whether or not I think it's actually a good idea and if I'm having fun or pulling my hair out. And I'm currently targeting Turing with it. I haven't actually enabled the encodings for Maxwell and earlier. Mary has a branch for Maxwell that she's been working on, but it's still kind of in process. I don't think you can really pass much, but she's got some of the basic stuff in coding. But yeah, more compiler stuff in the next talk. And yeah, we're passing a lot of CTS tests. We're currently at 400,000 tests passing with 0 fails. We'll just highlight that number. That is as of the Valve dinner on Monday night. I finally got the result in. So yeah, we are in very, very good shape. I will be submitting conformance immediately after the talk. So that's, yes, we have, and that is with Vulkan 1.0 specifically. We are not to 1.1 yet because 1.1 requires subgroup support, which I have not enabled in the new compiler. Also, these numbers are with the new compiler, not the old one. The old one does not able to allocate registers well enough to pass the CTS. The new one can. So things are looking pretty good. Does NVK run your favorite app yet? I don't know. Go ahead and try it. The reality is that I've been focused on trying to get the driver written and not trying to test all the apps. Different people have different ways of approaching this sort of thing. I'm very much a CTS first developer. Some people are very much app first. But I do know that some apps do run. And I was demoing at the Collabora get together earlier this year with a couple of racing games and Hollow Knight I had running as well. So there's some games that do work, but I don't know if any particular one does. That same thing applies to, games on Zink and basically anything else. Like, go ahead and give it a try, but I don't know. What do we advertise currently? Vulkan 1.0. That will get eventually bumped up. I'm hoping that we're bumping up to 1.3 before too long, but like I said, there's compiler stuff that needs to be done. We need to do subgroup operations. We need to verify that the memory model works. There's a bunch of other stuff, but we are, like you saw on the feature slide a little while ago, we have most of the features to get there. It's just a matter of getting the last few gating bits to be able to click off the versions. When are we going to get Vulkan? Okay, that's my question. When are we going to get Vulkan 1.3? So soon, very soon. So yeah, that's NVK. And then I will let Karol, wow, brain's not working. I'll let Karol do a couple of community updates.
Yep. So I don't know if everybody here saw this email from Ben, but Ben effectively resigned as a Nouveau maintainer and developer. Ben has been doing a lot of great work on Nouveau, enabled done a lot of hardware enablement, recently worked on GSP support. So most of the code you will see merged for GSP is all Ben's work. Well, plus some fixes on top of that done by Lute and Danilo probably, but I think mostly Lute is working on that. But yeah, it's sad to see Ben go, and he will be missed by everybody, I guess. So, yes, so Ben stepped down. Lute and Danilo will cover the kernel bits going forward. Danilo landed or worked on the new UAPI bits Faith was talking earlier about. Lute will mostly focus on display-related things, so in case you're running into issues in one of those areas, you can reach out to them. Faith will be maintaining the NVK driver, obviously. And through all the work on NVK, we got a lot of new contributors. Some of them contribute code, others contribute in terms of testing and making sure their favorite games are running. So this is a big help, and it's good to see this change, because in the past the Nouveau community kind of shrank down and more people were going than actually, coming to the community. So that's really good to see. I will be mostly focusing on maintaining the OpenGL driver. And if anybody of you is interested in helping out in any way, please do so. Testing is much appreciated. A lot of the stuff I've been doing in the past is just tracking down regressions. So if you have some time and want to test new kernel releases early with your NVIDIA hardware, please do so, and file bugs, and then we will be taking care of those. So I've also asked for some questions beforehand on Mastodon, and I think one big question which will also come up in the future a lot is what do we do about CUDA? Because that's kind of, with NVIDIA, and people are just interested in seeing this happening. And I think it's really complicated to answer. Nobody of us currently has actually time to work on this. And from MISA and also compute ecosystem point of view, it's kind of a weird target because it's a closed API. We can't really do anything. We just have to eat what NVIDIA is throwing at us. So the motivation to actually work on this is pretty low. If anybody has spare time and would like to do a MISA implementation of CUDA, they can work on that. And if they submit an merge request at some point, it might get reviewed and merged. But yeah, I think it's just it's unknown what will happen in this term, in this regard. So users are also asking if their next GPU should be NVIDIA, which I think that's kind of an upgrade answer to what we had 1 or 2 years ago, because then it was a straight no. But now if you want to help out, you can get a new NVIDIA GPU. If you expect things to just work out of the box and get great performance and everything, then maybe try in 1 or 2 years. Performance won't be great until GSP is merged. NVK is also not really optimizing for performance right now, so things are pretty slow. But yeah, we will get there eventually. So, any other questions?
Hello. Is the plan to keep the existing Gallium GL driver around, or is the plan to start using Zink?
I think the plan is that we don't have an answer to that right now.
Okay.
I think I'm pretty vocal about torching the OpenGL driver. I think that's not a big secret if you are following what happens on the IRC. And I think we have to keep it because of old hardware. And the biggest problem is that the OpenGL driver is split in 3 parts. We have the NV30, NV40, and NVC0 driver. And originally, I kind of hoped we could torch the NVC0 one, which is Fermi and newer. The problem is that Fermi Wilkinson powered will probably not happen until somebody with a lot of time and dedication is working on that. That's unfortunate because it kind of means we have to keep all the drivers. But we might be able to remove some of the new hardware support once Zink actually provides benefit to users. We could also start to use the new compiler with the OpenGL driver, which would also fix a lot of bugs. So I think that's kind of the overall situation.
Yeah, I think overall, when we talk about like Kepler and Nouveau, I think we are going to burn the old driver to the ground. The question is whether it's going to be replaced with Zink, or if we're going to decide that it's actually worth it to write a Gallium driver at some point. It shouldn't be hard to write a new Gallium driver with the components that I've built for NVK, but there's a lot wrong with the current one. And it probably needs to be started from blank files if that's what we want to use. And the question is whether it's worth doing that over NVK or over Zink. And I don't know that we have a solid answer to that. Like, if Zink is working well for users, we probably won't bother, but.
So I noticed on your impressive feature page slide that you have several features related to sparse. And I'm just curious how you managed to write an entire Vulkan driver for reverse engineered hardware, plus a new compiler and an image layout library, supporting sparse, faster than Intel could support sparse.
That is a question for Intel, not for me.
I don't think the new NVK driver is really that much reverse engineered because we actually and NVIDIA actually released header files for all their acceleration blocks on the hardware. So we have at least all the names, and there's also sparse in some of the names, I think.
Well, I mean, the sparse doesn't really show up in the headers. It's more about like image binding and memory binding. But it is true that like NVK isn't really properly a reverse engineered driver because we did have all of the headers with all the things. I had Nouveau GL to look at as an example of how to set up the hardware and get it initialized. So like my start was basically look at Nouveau dumps or look at what Nouveau is doing on the GL side and just kind of do that to get started. So we weren't really starting from zero. So that's part of why we've been able to go as fast as we have. But some of it is just because, frankly, the Red Hat kernel people have been amazing. I told Dave I need a new UAPI. This is what it needs to look like. And about 6 months later, there was a merge request sitting there with NVK changes. And about 3 or 4 months after that, he's like, yeah, you should test this out and let's try and get it merged. That's much, much faster than I had experienced with the Intel kernel team. But yeah, so they've been fantastic to work with. I didn't have a call-out slide, but Danilo has been amazing. Ben has been working hard. I haven't interacted with Ben much, but he's been working hard on he was working hard on the GSP stuff. Dave has kind of been coordinating things. We've had a bunch of contributors. We had Mary has helped out with some of the stuff to get Maxwell enabled, and she's helping me out with Mac right now. We've got Thomas and George, and I'm trying to remember who else have just showed up in the community with merge requests. That has been amazing. I had Mohammed over the summer. He did YCPCR. We had, I'm blanking on names. I am bad at this. I should have put it all in a slide. But we've had a bunch of people who've shown up and done work and been helped out, and it has been fantastic. It's great, really great to see community coming up, and everybody's been pretty good. People bug me about VKCube a little bit too much, but it is working now. Other questions?
Not a question, but more of a comment. If you are interested in working on Nouveau, we are hiring Red Hat as well as a replacement for Ben, and partially is going to work on Nouveau as well. So feel free to reach out to me if you are interested.
I don't see any more hands, so I think we'll go into the break. And then...
we could be together, baby, as long as skies are blue. You act so innocent now, but you lied so soon. When I met you in the summer,
brothers and sisters, love between nations and nations. When we get together, we'll have peace and joy. We'll have understanding of one another, united as one. Right now you should be feeling the freedom of this music. Right now you should be feeling the vibe of this song. Everybody
we go. All right, test, okay. Hello everyone, so welcome to my second talk today, which this time we're talking about backend compilers written in Rust. So a little bit about me. I didn't do this in the last one because it was a shared talk with Karol, but my name is Ekstrand. I have been kicking around free desktop for over a decade now, which feels a little bit weird to say, but there it is. I was at Intel from 2014 to 2022, and I have been at Collabora since January of last year, where my job is basically to do anything in the Linux graphics stack that makes Linux graphics better. It's a pretty awesome gig, and I'm very thankful for it. But what that has meant for the last year and a half is NVK and fixing the NVIDIA problem, because we have an NVIDIA problem in Mesa, and it's making us look pretty bad, if we're honest. And so I've been working on trying to fix that, and that has meant building NVK. That's also meant building a new compiler, which is what we're going to talk about today. So yeah, that's me. And so let's get into the talk. So for the most of this year, I have been working on NAC, the NVIDIA Awesome Compiler, which, yes, I did intentionally name it to get that acronym, but it wasn't too much of a stretch. This is a brand new backend compiler. It's been written from blank files. I did not really use much of CodeGen. I have looked at like the actual code emit part of CodeGen to figure out like where the bits go in the different instructions, and a few other things. I've definitely looked at the output of CodeGen as a reference quite a bit, but it's a brand new compiler. It's been written in Rust, which is what we're going to spend a lot of today talking about. It tries very hard to be a model mirror user, trying to like not make the mistakes that I've seen made in other compilers over the years, including the Intel one that I worked on for a long time. Part of what that means is it does a lot of lowering, and it tries to keep the backend very, very simple. So I make use of the backend 1, backend 2 no text sources to completely lower my texture operations. So by the time it gets into the backend, it's basically exactly what the hardware wants, which I think is going to end up being a lot easier for us to manage different hardware versions, because some of the sources do move around a little bit between hardware generations, but all of the hardware generations take 2 Vec4 sources, so it still maps very nicely. It's just that that code will have to be a little bit different. But it's going to be easier to deal with that in Node than it was in the backend, or at least much easier than the way the old backend tried to deal with it. So there's some other things we do. We do some I/O mapping in Node. That was something we had to figure out for geometry shader. We started doing geometry and tessellation shaders in the new backend, because NVIDIA does some funky stuff when it comes to per vertex I/O. And it was easier to lower that stuff in Node. So we try to do as much lowering in Node as we can and keep the backend simple. The backend is still not simple because it has a register allocator, but it doesn't have to handle the same kinds of transforms that Node does. All the Node passes are written in C. This is another sort of keep the backend, to keep things simple thing. If you're trying to do a bunch of Node manipulations, doing that in Rust is not going to work real well. Karol has done a little bit of that for Rustical. But it's been a little bit tricky. And for me, I felt that it was, at the current moment, we're really not ready to do that stuff in Rust, and I wanted to do it in C. And it is also a fully SSA compiler, all the way into register allocation. So I decided to try and do that, and took the plunge, and it has worked out actually quite well. And one of the results of this is that we have a register allocator that actually works. We do not randomly fall over because we tried to spill and failed. It actually works, and as far as I can tell, it works robustly. When I was figuring out spilling, I was running the full Vulkan CTS with 16 registers available and passing everything that I was passing before. So I think we were in a pretty good situation there, which that was one of the big challenges we had with the old Nouveau compiler. If you try to run the Vulkan conformance suite, you will not actually get it to pass, because there are a couple hundred tests that it just goes, I couldn't allocate registers this time, have fun. And it just doesn't give you a shader back. So things are in pretty good situation there. And it is fully SSA, which means certain optimization passes are easier to write and things. It also means we have to do lots of coalescing, and most of that stuff isn't really tuned yet, but we should be able to get there. So why Rust? That's an obvious first question. So C is terrible. We all know this. Those of us who prefer C over other languages know it better than most. It has a lot of limitations. It's a good language for the problem that it's solving. Compilers is not really the problem it was designed to solve. C++ is also terrible. You can disagree with me if you want, but you're wrong. C++ is a terrible language and it has all sorts of problems. Rust is less terrible. I'm not going to say Rust is also not terrible, because I think all languages are a little bit terrible. But Rust is, in my opinion, less terrible. It has a powerful type system, which does not rely on virtual dispatch, which is useful, because function pointers can be a performance headache if they end up in the wrong spot. It has a very... and its type system is also generally more powerful than C++ as well. You can build anything you want to in C++ templates, but like the facilities they have built in are really nice. Like they have traits and a bunch of other more modern language features that are typically reserved for languages like Python or Ruby, but we actually have them in a compiled language and they work performantly. It has a large, well-thought-out standard library, so I have hash maps and all these container types that I need. Those are all built into the language. An annoying amount of, there's a lot of stuff that's in crates that I wasn't able to use, but like there's still quite a lot in the standard library. And it has this fantastic bio checker that actually catches bugs. And that's been, we'll talk more about that later, but the bio checker is very much my friend. Wait, that's the next slide. So one of the big complaints people have with Rust is that they're constantly fighting the bio checker. And this is true when you first start off using the language. It's really easy to get frustrated, but you kind of have to lean into the curve. Learn to embrace the biochecker, make friends with it, and the biochecker will help you find bugs. I have written bugs into my code several times in different compiler optimization passes, which the biochecker caught for me. So it is actually a very good code review buddy if you learn to work with it instead of working against it. And it does mean your code is structured differently. That can be a challenge, but if you sort of lean into it, most of the time it's your friend. There are definitely certain types of things that it makes more difficult. Graph data structures in Rust are not the easiest thing to do, because you don't have real pointers most of the time. But it can, for most things, make things better. So why is NAC a good candidate? For one thing, it's very, very self-contained. We don't really need to call out into the rest of Mesa. We need to parse ner, that's a whole challenge. We need to, but otherwise, it's basically just doing a bunch of compiler passes and dumping out a binary, right? And it's really easy to pass arrays of bits back and forth between C and Rust. Less so complicated data structures, and so it makes for the fairly small interface point. The entire interface between my Rust compiler and C, if you just ignore no, just set that aside, forget that exists, the entire interface is 7 function calls. So this is very, very straightforward to go ahead and code gen, to bind gen rather. As opposed to like when Karol was building Rustical and we were trying to bind gen all of Gallium. Like that's a lot bigger interface to have to deal with and debug, whereas 7 function calls is pretty straightforward. On the no front, the important thing is that we only need to read no. So if you go back to my earlier slide, one of the things I said is that I do all of my no passes in C. Well, by the time I get into Rust code, my no is entirely read-only. And that solves all sorts of Rust interface problems. Because I don't have to think about mutable references, and I can make it all pretty happy and pretty safe. So, can you write a compiler in Rust? That was the question that I really wanted to answer with NAC. We've been trying to integrate some Rust code into Mesa. We'd had Rustical. That was kind of I think overall it was probably a win, but it's kind of hard to say. Because the amount of bind gen pain that we have to deal with in order to implement OpenCL and then bind to Gallium is kind of a lot of headache versus the headache solved by using Rust rather than C. But I think it came out okay. It works well. But in terms of was it worth the trade-off, I think that's a harder question to answer. So I wanted to see how things would look for compilers, because compilers have a different set of problems to solve. And generally, I think the answer is that yes, you can, and that, yeah, it's actually a pretty good idea. Again, you have to make friends with the biochecker. That's, if you're not willing to get along with the biochecker, you're going to have problems, but this tends to mean lots of hash maps, which is mostly okay if your stuff hashes quickly. Most of my key types are either integers or things that you can very easily pack into like 64 or 32 bits, so hash maps work out pretty well. It does tend to mean you do some struct of array where you might do array of struct. And this is just because depending on the order in which you need to access things and what things you need to access as mutable, it's easier if you can structure stuff such that you have one array of stuff you're reading and one array of stuff you're writing, as opposed to an array of structs where you read one field and write another. And so you tend to end up splitting stuff out a little bit, but it's maybe not as bad as you're thinking when I say that, but it does mean you tend to do that a little bit. So the first challenge in this whole mess was, how do I actually read No? No is not Rust-friendly code. It uses a lot of very tightly linked data structures. It has pointers to pointers to pointers everywhere. It has intrusive linked lists. None of these things make Rust happy. The key is to make it read-only. And when it's read-only, then you can have a reference to the shader, and everything else borrows that reference to the shader, and you can keep stuff safe that way. So basically, you treat the no shader as one big, giant data structure. And then I have some Rust wrappers for No. So we use traits to add methods to no types. We could probably do that differently if we did the build system stuff a little bit differently, but bindgen plus Meson is kind of weird, and so we have to add our methods using traits. But we have things like, if you have a no block, you can do mb.iter_insters, and that gives you an iterator, and it iterates over the instructions. Karol wrote a lovely little iterator for exec lists, which we're using. And so you can just iterate over your instructions just like you would any other container object in Rust. For things like sources, I implement a sources as slice method, and that gives you a slice, which is an array, basically it's a pointer plus a length, is what it is under the hood, but it's a safe data structure that protects you against array overruns and things like that, so we can look up the no op info, get the number of sources, take the pointer, turn it into a slice, and then hand that, and so that in most of our Rust code, we're just iterating over the slice and everything is safe. For like constant sources, I implemented that using something that returns an option, which is a very Rust paradigm. And again, it gives us the method that we have in No is like we have no source as const, and then we have no source as uint, and there's this little dance you have to do. I made that a little bit more Rust friendly. And the end result is that I have very, very little unsafe code. There is a little bit of unsafe code, but it's mostly around like so there's some no data structures that have unions in them. There are some places where I need to like cast a tiny little struct that's 32 bits to a uint 32 or back in order to make no happy, and that kind of stuff ends up being unsafe. But for the most part, the code that reads Rust and turns it into NAC-IR is Rust safe, which is something else that I really wanted because I didn't want to have like piles and piles of unsafe blocks all over my parser. I've been able to keep them very, very tightly contained. So that's worked out pretty well. Again, the key to this is No is read-only. Like the moment you try to write No, you're just kind of toast when it comes to safety from a Rust perspective, just because everything is so tightly interlinked, and Rust's reference borrowing model doesn't play nicely with that. But if you treat it all as read-only and you just treat it as one big giant container object, it actually works pretty well. The second challenge, and this is something that took me quite a while to sort out, is how I wanted to deal with instruction sources. So when you are trying to represent code in data structures, you have instructions, and they typically have opcodes, and they have sources and destinations, and anybody who works in a compiler is familiar with these things. And I wanted something that was maybe a little bit better than what we've done in the past. I really wanted instruction meanings to be very, very clear. So if you look at like no, we just have an array of things, and you do inst.source3, and that's what you're looking at. But nobody knows what 3 means, and 3 depends on the opcode, and it's kind of a mess. I didn't really like that. I wanted to see if we could do it better. If you look at the CodeGen compiler, things got even worse because then they had sources that had indirects, and that was its own special thing. It was a mess. At the same time, I want fast generic access to sources. I need to be able to do sources 3 so that I can write a copy pass that just walks over all of the sources and does a thing. So there's kind of a bit of a mismatch there. I also wanted to avoid extra memory allocations. So one of the obvious, so you typically have, most instructions have like a bounded number of sources, like 4. But then you have instructions that are more complicated, like you have parallel copies that need to be able to have 72 sources depending on how many registers you have going through them. You have phi nodes, some of these things. And so we need to be able to handle more than just like a fixed number. And then you have an array allocation problem. Like, where do you put these? Do you put them in a vec? Do you put them in a fixed locations? And how do you avoid making every instruction have an extra allocation tied onto it? So like in the Intel backend compiler right now, at least in the scalar one, every instruction is an allocated thing, and then it has an array of sources, and that's also an allocated thing, and that ends up being a lot of memory allocation. We also need to handle things like predicates and indirects. We need to handle modifiers, all of the usual graphics things. So there's a couple places I looked at as prior art. One of these is no. So no source stores, for the most part, sources as arrays. It really depends on documentation to know what different things mean. So if you go look at no intrinsics.py, every single intrinsic will have a little comment that says, here are the sources. If you ALU instructions, you look at no opcode.py, and it's got like a description of the ALU instruction there with constant folding code. Everything is by convention. Const indices are a little bit better because we added these tags and helpers for fetching them, but it's still kind of similar problem. And basically, all of our correctness is ensured by no validate. We don't really get anything. There's no type system that we can use to guarantee us anything. So not a great situation. I also looked at Akko, which they do some really clever things in there, which I was very impressed by. They do have, like, for the most part, each instruction has its own type. Maybe there's some duplication there, but they have piles and piles and piles of struct types to handle the metadata stuff, which, fair, that's reasonable. But sources are still arrays, and each one of those instruction type has a little comment that says, source 0 is this, source 1 is this, source 2 is this. And to avoid extra allocation, they have this fantastic little data structure called Akko span, which I really like, where it basically gives you unsized arrays, but you can have more than one unsized array, and it doesn't necessarily have to be the end of your allocation. And it gives you, O of 1 source access, C++ iterators. You can have lots of sources and lots of destinations, and it's completely unimplementable in Rust. I really, really wanted to do an ACK span, but I couldn't figure out how to actually make that happen in Rust. So the question is, how do I do this? And I want lots of things. I want to, for one thing, I want to take good advantage of Rust enums. So Rust's enum type is actually a tagged union, and I wanted to be able to take advantage of that. It's much, much safer than No's plan of just have a pointer and a type at the beginning of it and check the type and cast. That's not a good plan, but it works pretty well. But the Rust enums are much safer. I wanted descriptive names for sources if I could. So like source 0, source 1, source 2, it does work, and I would have done that in the end if I had to, but I really wanted to get descriptive names for sources. I wanted type-safe metadata. I really wanted Rust's type system to help me out and check things. I didn't want to just validate everything if I could avoid it. And again, I wanted like the generic O of 1 source access and these things. Well, you can't always get what you want, unfortunately. But if you try, sometimes you can get what you need. And that's really turned out to be true. So let's look at an instruction. So this is opcell. This is the select instruction. It has a destination. It has a predicate that is the condition on which to select, and it has two things to select between. So as you can see here, the destination has a name. I'd call most of my destinations dest, but I could call them something else if I wanted to. And I do take advantage of that for, like, I add 3, I think. I have, like, the carries named. The sources are named, and they have different names. So I can have the condition as cond, and when I'm in my code and I'm looking at an op select, I see condition, and I see sources as 2 separate things. I have these type decorations. So the first one is a predicate, so that's a 1-bit register. The second one is what I'm calling an ALU, which means ALU in this context means that it can take immediates and constant buffers and some of those other things, but it can't do source modifiers. So that's all declared right there in the struct definition. And then I have these derive macros. Derive dest says slice and sources says slice. And these do magic. In particular, they do this magic. So every single one of these opcodes implements this, which gives you all of the sources as a slice of sources, and it gives you, or you can get it as a mutable slice of sources. You can get the source types as a source type list, which isn't an array, but it kind of acts like one. And same for the destinations. And then on my op enum, each one of the opcodes, so fadd contains an op fadd, so that's the data structure. And the enum itself also implements those 2 traits. And all of that is done inside of a proc macro. Coming back just a little bit, the proc macro relies on a few things. So it has to be rep/c, and the proc macro will check for that and compile fail if it's not. And all of the sources have to be consecutive fields, and all of the destinations have to be consecutive. So you can't have like a source and then a destination and then 2 more sources in your struct. You have to keep the destinations together and the sources together. But that just guarantees that everything is contiguous in memory and lets me actually give you a slice. But the proc macro will check all of these things. It will check data types. And unless you do something crazy like hide a source inside of a struct type that you then put in something, the proc macro will compile fail on you whenever it's not able to generate a safe implementation of my as-slice traits. And what does that let us do? It lets us write code like this. So this is from dead code elimination. And the important thing that you can see here is the predicate on the instruction is handled specially because predicates are a little bit weird, and I decided to keep those as a separate thing. But all of the other instruction sources, back up just a little bit. That predicate is not the same as the condition predicate in the select. That is the entire instruction predicate that determines whether or not the instruction actually executes. All of the predicates are just regular sources. But yeah, I can handle all of the sources using an iterator. I can just do for source in instru.sources, and off we go. And also because we are using our own struct types and we have an enum wrapping struct types, we have type-safe metadata like I wanted. This gets us almost everything on that list. So I'm able to use Rust enums to get type-safe access to metadata and sources. Sources have descriptive names. I have O of 1 source access, which works with all the iterators. And, oh goodness, I am running out of time. The only thing I don't really get is the type system checking my stuff. I also, hopefully, the put op lookup is actually basically just a lookup table. The other thing I want to talk about a little bit, and I'm going to go through this quickly, is how we represent values. So I need to be able to represent SSA values in registers because we do register allocation before we go into code gen. We need 64-bit values and vectors. We need predicates and GPRs, all of the usual stuff. The way that I have done that for SSA values is that each SSA value is a single 32-bit value. And it's got a reg file and an index, and it packs into 32 bits, so it's cheap to copy around, and you can easily hash map it. An SSA ref contains up to 4 SSA values, And the register allocator does magic to make sure everything's consecutive once you get into backend. And Daniel is looking at me and smiling. I haven't actually talked to Daniel about this, but I've talked to Alyssa about Daniel's plan for ACO and did that. We also have a few other source types. We have register references, we have constant buffers, which basically any ALU instruction can do a uniform pull, which is kind of awesome. We have immediates, and we have some special case immediates that are sometimes allowed when other immediates aren't, so they're special cases. And then a source and a destination is just an enum that wraps one of these things. So it's like an enum, SSA gives you an SSA ref. And so, again, we're using the tagged enums and match instructions absolutely everywhere to figure out what's in your source, which is a little bit better than look at like a immediate register file and then poke at bits in a union. The other thing is, the other big challenge was instruction lists. How do I do that? I ended up using vec of box, which is basically what ACO does effectively. And it's worked out pretty well. We can't really do no's linked list thing because linked lists and Rust do not work well together. Vectors and Rust work fine. Everything's good and safe. You can't insert in the middle, but that's mostly okay. There's a few challenges around that. Let's see here. Yeah, so there's a few challenges around that. There's a few workarounds. One is that you can split a slice. So vectors act as slices, and you can take a slice and you can say, here's an index, give me all the stuff before and all the stuff after, and those are separate things, and so you can have two mutable references that way. It's clunky, but you can do it. Another thing that you can do is you can use indices as if they're pointers and do vec of I all sorts of places. It's not great. The better thing to do is just to restructure your pass to avoid mutability in bad conditions. One way of doing this is I have this helper called mapinsters that's provided by shader, function, and basic block. And it provides a easy method for instructions for passes to just take, here's an instruction, and it produces 0 or more instructions that then end up feeding into it. And the mapinsters helper manages throwing away the old array, allocating a new one, and doing everything in a way that doesn't involve any O of 2 expands necessarily. It's fairly efficient. And it looks like this to use. So you just do this. The self in this case is a no shader. And so I just do my lower, it's called lower vec split. I renamed it recently, but there's some cruft in the code base, and that name is one of it. But you do just self.mapinsters, and you give it a function callback, and you just match with the instruction and give it a new instruction back out. And you just sort of do this streaming thing, and that solves all your mutability problems. It does mean you can only look at one instruction, but for the purposes of doing simple lowering passes like this one, it gives you what you need. Some more complicated passes handle this logic, where they just create a new vector and they replace it. This isn't as safe because it means you have to remember to replace the instruction list when you're done. And if you forget that, then you end up with a block with no instructions, and that's bad. But we do have to use it in a couple of places. The big thing that you end up doing here all the time is what I call the gather modify pattern. So instead of having a pass that looks at previous instructions as its modifying instructions, you do one pass that sort of gathers all of your metadata. So in copy propagation, that pass will go through and fill out a big giant table of here are all the copies that I see. And then you have a second pass that goes through and modifies, and the second pass can use mapinsters, or it can do something simple, where it's basically only looking one instruction at a time. And that allows you to avoid some of the safety issues where you might have, where Rust doesn't really like giving you a mutable reference to something, and then other immutable references around that. And it's actually safer. So this is one of the places where Rust's modifying your passes and things to force into Rust's biochecker model actually gives you safety and prevents bugs. I can't count the number of no bugs where somebody's written a pass and they have saved off a pointer to an instruction and then modified that instruction and then looked at it, assuming that it was the original. And Rust just prevents you from doing this for the most part. or at least it prevents you from doing it by accident. And so this is one of those places where I think just leaning into the borrow checker really does actually make your compiler better. It does mean restructuring things a little bit differently, but yeah. Hash map is your friend, like I said. You end up using it a lot of places. SSA value I have as hash mappable because I use it as a key all the time. I'm going to mostly skip the control flow graphs because we're running out of time, but graphs are generally a pain in Rust. My solution to that is I have encapsulated all of that pain into a single CFG data structure, and that CFG data structure is completely generic. There is no knack code inside that CFG data structure, so if anybody else wants to write a Rust compiler, they can just steal it. And it does all of the useful no things like calculating dominance and loop nesting and all sorts of good stuff. And then it basically just acts as a container data structure. I use a CFG of basic blocks, but you could also have your basic blocks in an array and just have a CFG that you construct on the side temporarily if you wanted to. It's kind of up to the user. Spilling and RA we're just going to not talk about because that's an entirely other talk. But yeah, so final thoughts. Do I like working in Rust for compilers? Yes, I do. I love working in Rust. It's a fantastic language. It's fun to write. It gives me kind of those Ruby feels in terms of fun, but without all of the shoot yourself in the foot. And it's been really great to work in. Enums are awesome. I don't recommend using proc macros for everything, but in the few places where you need a proc macro is an extremely powerful tool, and it's how I'm able to do like the sources as slice stuff. Traits and generics work really, really well. I really like Rust traits. Rust generics are so much nicer than templates because you can bind them to traits and guarantee that your code actually compiles before you try to instantiate it and get 3 pages of error messages. Having a standard library is nice. I am just using the standard library data structures for everything. And I really find that Rust abstractions have worked out really well. It's taken me a little bit of time to get there, but I think the end result has been good. We'll skip most of this, but again, borrow checker is your friend, not your enemy. Learn to use it, lean into the curve. It's a good thing. Also, implement from for everything. From is awesome. It just lets you do easy casts. And you should implement it on all sorts of stuff because you'll need it. So like I have a from implementation where I can just do a 32-bit integer value .into and put it into a source. And all of the trait magic just makes that happen. So there's the end of it. Any questions? Also the obligatory we're hiring slide.
Yeah, thank you for the talk, very interesting. I was wondering how the development of this looked like because it was kind of uncharted territory. So did you end up making incremental improvements all the time, or did you end up like rewriting a few, like doing like 3 rewrites because your understanding of the problem changes over time? So
at the beginning, there was a lot of rewriting, and there has been quite a bit since then as well. But I knew that some of these problems were going to be particularly thorny, and so I solved them up front before the compiler got too big. Like figuring out my proc macro and the sources as slice stuff and how I wanted to organize all that. That's something I did very, very early on when I only had a half a dozen instruction types, precisely because I knew it was going to involve a lot of refactoring. But one of the other nice things about Rust is that because of how powerful the type system is, refactoring is not as hard as it would be in other languages. Because if you set your types up properly, you can kind of, like, if it builds, it probably does the same thing it did before. And so you have a little bit more confidence when refactoring stuff than I would have if I was refactoring C. And so I have done a lot of that, and I'm still doing some refactoring, like from on immediate types is something that I just added and I went through yesterday and I replaced a bunch of stuff with it. But for the most part, like after the first couple of months, it's kind of remained the same structure. But yeah, there definitely was some of that early on as I was trying to figure out some of the very basic things.
I wanted to ask how was your experience with the procedural macros development?
Proc macros are a bit of a pain. So there's sort of three problems I ran into. One is just that the documentation around them isn't awesome, and it just kind of took me a while to figure out how to do it the right way. The second is that the Meson build system and proc we have less support in Meson. Proc macros, if you're going to do them properly, requires 4 crates. Pulling in crates is not a real well-defined thing at the moment, and the way that I'm doing it is that I actually have forked the crates into my own GitHub and added Meson build systems to them. Dylan actually did most of the work to add the Meson build systems, but I've had to fix some bugs with it. That's all improving. Like, well, Dylan and Dylan Baker and Xavier Classi Dylan's at Intel, Xavier's at Collabora. They have been working on trying to sort those problems out and make Meson more Rust-friendly. Hopefully all that stuff will be sorted in time for me to land NAC soon. So that's been another problem. And then the third problem is that at one point I ended up doing something that the older version of Proc Macro 2 couldn't do, and I had to upgrade the Proc Macro package. And that actually broke some stuff because they changed their API somewhere in that process. But overall, it's worked pretty well. And for the kind of thing that I'm doing, if I was to try and do that in C, I would be writing a Python script that tries to read C code. And that is just not a robust solution for anything. So when you need a proc macros are a really good solution. But generally, they're maybe not something I would recommend people play with.
Hi, thanks for the presentation. I just wanted to confirm that I understood correctly. So basically, you cannot mutate NIR. So basically, you transform that into an intermediate representation that you can then mutate, and you run the optimization passes on that.
Yes. So I have my own internal representation. Those structs that I showed towards the beginning are part of that. I also have basic blocks and functions and shaders and all of that stuff. And all of that is very Rust-friendly data structures. It's all vec of struct, and those are fairly safe. The reason why I don't want to mutate NIR is because NIR is very much built around, it's very much a graph data structure. It's very much built around pointers going every which way, and that's not Rust-friendly. So yeah, the IR in the back end is very Rust-friendly. It's designed to be Rust-friendly. And I have to translate from NIR into that before I do any modifications. But I do have several optimization passes in the back end.
Thanks. Yeah, another question is, in traditional compilers, usually one of the biggest issues is dealing with module imports and exports, so linking compilation units. Don't you have that same issue here?
Typically, any sort of linking that we would do happens in NIR quite a lot earlier than when we get into the back end. At some point, we will add real function support and not just assume that there's one function for everything. That will have a set of challenges with it, but most of the stuff around linking and combining things together, that happens at a higher level and I don't have to worry about it.
Okay, last thing, I know that you mentioned that register allocation is a bigger issue, but what is the biggest problem that you have with register allocation? It has to do with Spillington memory or too few registers?
The biggest problem with register allocation is register allocation. It's just a hard problem. Like, there's spilling, which is its own set of problems. There's register allocation, which doing it in SSA actually makes it quite a bit easier. I don't have to do any, like, my register allocator is linear time-ish. I don't have to solve any NP complete problems, which is nice. You have to, but you do have to do register coalescing as you allocate and try and allocate things efficiently. Because otherwise you end up inserting a bunch of moves to shuffle stuff around. Some of that I've already dealt with. Some of that is still a problem for future me. Yeah, there's a lot of stuff in there, and that's why I tried not to get into it. But yeah, the whole field of register allocation is kind of a mess on GPUs, and there's been a lot of discussions in talks and sideband about the problems there. But yeah, that's something that maybe would be a better hallway conversation, I think.
Yeah, sure. I was definitely just interested in understanding what the complications are in register allocation GPUs versus normal CPUs.
Yeah, there's nothing Rust specific about that, but there definitely are complications there.
Okay, we can take that to the hallway. Yeah, thank you very much.
Hello.
Hello
When
again.
are we getting NER3 and Rust replacing all the Python scripts with macros?
Probably never.
If there's time for a few more questions, I wanted to ask if the compile times, if you imported so much libraries, were very high or low.
Compile times for the Rust code are reasonable. It's a little hard to tell because Rust is a monolithic compile, and so it ends up, like the way Meson invoking Rust works, ends up looking like Rust takes a while, but in C or C++, that would be spread out across 10, 20 files in your list of things. But overall, the build time for my entire pile of Rust is less than a second, so it's fine. I don't see any more hands, so do we have any questions on the matrix that we need to talk about, or are we good to move on to Alyssa? Nope, no more questions. Okay, thank you very much.
front, left, front, right, front, right, front, left, front, left, front, right. Front, right, front, left, front, right,
And I'm really lucky when she helps me with the magic, which doesn't, it happens whenever it's convenient to her, which is almost never. She's my familiar. She's a cat. So give it up for the cat, who does not want to help unless it's convenient to her, and who will be doing the presentation if I can't. But it's telepathically, so you'll have to also be a witch to understand it. So if you don't hear anything, that's on you. I'm sorry, I can't translate. Also, any Linux audio people in the crowd, great excuse to use there too. But we're getting there. Cool. Well, we will be talking about the Linux on the M1 effort. I can say ahead of time that we've achieved a lot since last year. We went from basically nothing working, and you were all impressed by GNOME running last year, to we are now a conformant driver. Like officially conformant, like Kronos recognizes us, like we can use the OpenGLS trademark, which I totally should. Anyway, GLES 3.1, currently working on 3.2, and we're going to talk a lot about that today. It's not in the slides, but Karol should be out there in the audience somewhere, probably. Hi, Karol, yes. Karol went off and did OpenCL on Asahi, and I don't know, apparently most of the CTS passes and GPT-2 runs, is that right? I'll take it. They're 2,000 tests. That's pretty good. That's like an A+, Yes. Yeah. Somehow managed to pass CTS without a spiller. Don't think about it too hard. Glass CTS is an interesting bunch. Vulkan will not be so kind to us. And we will talk about Vulkan will not be the subject of this talk. Very sorry. So yeah, we still going? Okay. At any rate, as it seems I will still be stalling, and I ran out of kitty-related material. I don't know. Not really sure what's happening here. Magic is a very fickle thing. I would just wave. Sometimes I wish I could just wave my magic wand to make the tech difficulty go away, but no. If the cat did it, it might work. She's better at this than I am. But anyway. I should clarify some additions to the outfit. The wand is real magic, the cat's real magic, the hat's just decorative. In case anyone's been wondering. But that was a good sign.
Can you hear this? Can you hear this? Can you hear me? Can you hear some feedback from you? Are we trying to use this to? No, we can use that. I was just going to use my. Okay, so you can use. Hello? Hello? Is it also doing? We are not listening. Can you hear this? Can you hear this? Let's try the other interface. Can you hear this one?
And I guess we might as well talk about Vulkan while we're waiting as well, because there's not much in the slides. But this is the #1 question we get asked: when will it run Vulkan? Second only to when will it run Steam. But those are kind of the same question, honestly. You know, somebody asked me today that I seem to think that DXVK is the most important graphics application in the universe. Which, fair enough, I do seem to think that. And they asked me name a single DirectX game, and I don't play games, I don't know. But Vulkan, I don't know. Karol did CL. I've been hacking on GL and the compiler and reverse engineering and all the other stuff. What's up with Vulkan? Well, we've got Ella somewhere out in the audience.
Oh, now it works. Now it works.
Am I hearing things? Sometimes you just hear it, you know. Ella's somewhere out here probably who has spearheaded the Vulkan effort. And we've got a bunch of other people who've been helping out with that, some of whom are here, so hello. We've got Rose. Have you done
I'm
Vulkan
hearing
stuff?
a lot of talking.
No Vulkan you. Mary's done some Vulkan stuff. I don't know. That's your turn. I did the reverse engineering and the compiler and the GL reference code. Now you get to write a Vulkan driver. It should be fun. Hey. And I don't know if I'm just supposed to run through my prepared material, but you know, trying not to waste too much talk time while having hallucinations of Lina speaking into the ether, which I'm actually quite used to. We have a lot of phone calls, but you know, it's a little different this time. Yeah. Any questions? Thanks for coming to the talk. I am happy to answer questions. I feel weird just standing here. Yes.
There's an IT assistant in the room who wants to help.
Sorry?
There's a computer engineer or IT assistant in order to help in the room.
I'm sorry, I can't understand.
It's a joke that there's no computer engineer in order to help.
Oh, yeah. Alas. Yes.
Commented that the hat's just decorative. What about the cloak?
We don't talk about the cloak. We've got video.
No video? Yes? Yes, video. Yes, video? Okay.
And I will let Lina take it away.
Good on that. Alright, we have, okay, I am hearing myself, but that's probably not much I can do about that.
Sorry. Sorry?
Alright, are we good?
I think so. Yeah, take it away. Lina. Woo.
We're live, right?
Can she not hear us? I'm confused. Should she? Lina, can you hear us?
Yes.
Okay, hi, yes. Take it away.
Alright, let's go. Alright, hello
last year talking about our little Rust driver for the Apple GPU, and we're going to give you a little update on how things are going. So yeah, last year when I did a talk, this is about where we were. So we had a desktop. We just had gotten things running. And at the time, that driver had, lovely things like blocking submit. So no sync. Who needs sync when you can just block for the GPU anytime you give it work? And we were shutting down the GPU every single submission because there was a bug with TLB invalidation, which is really funny. And even then, it was running at like, over 30 FPS. And that was only on the M1 originally. We didn't have support for the other GPUs or anything like that. So now, fast forward another year, and we are now conformant on all Apple Silicon GPUs, all the Mac ones anyway, across 2 firmware versions, because we have to support multiple APIs. We have explicit sync with firmware scheduling. We're actually faster than macOS for some workloads, I think Zonotic was running faster on Linux than macOS. The UAPI is Vulkan ready, and we actually have a work in progress Vulkan driver. And the kernel side is 18,000 lines of Rust plus the abstractions. So one of the cool things is that it's super stable. People always talk about like memory safety and Rust and all that, and how that can benefit kernel development. And so we really noticed that when we started, because we got from the first cube rendering on Linux to a stable desktop in just a couple of days. And I think that's pretty unheard of for kernel GPU driver development. So we've been shipping this to Asahi users since December. I've actually been streaming from an M2 since then, and I leave my streaming machine on for months at a time, and it's fine. And as far as I know, we've had 0 kernel oopses reported in the wild from users, excluding 1 DRM shed issue with Firefox, and not counting GPU firmware crashes, which are also rare. But the actual driver, the logic and the memory manage and all that, we've had 0, problems there. So last time I talked about the versioning magic that we have for the Rust driver. So we have basically conditional compilation, on a line, on a statement, or even sub-statement basis for different firmwares, because that way we can support multiple API revisions and different firmware versions in the same driver. We have without having to copy and paste huge structures and things like that, or doing build system level conditional compilation. So we have all the differences written into the same driver, and we support 3 major firmware API branches, I guess you can call them, across 2 different firmware versions. So G13 is M1, 14G is M2, and 14X is M2 Pro Max. And basically what ends up happening is that we compile every API-dependent part of the driver multiple times, and it works. So we even have some major changes between versions. So on everything before M2 Pro Max, most of the render configuration was in a big structure like that. So it's a lot of fields and a fixed layout structure. For G14X for M2 Pro Max, they switched to a register write list. And that's, it's still, these 2 screens are literally just adjacent in the driver. And there's the conditional combination at the top, and it works. And we can do major changes in structure layouts, and yeah, it's fine. It scales. So a few updates on Rust for Linux. So one thing is that we got rid of place. So say hi to Pin in it. We have basically we replaced. I used to have a big macro. I don't remember that. That was how was that? Basically, we had a big macro that was used to initialize CPU structures on the heap. And And that was a bit messy and kind of a, a hack from my driver. So now we have an upstream implementation of that called PinInit. And so that can initialize complex types on the heap, and it composes properly. There's no more unsafe or anything like that. And it's already upstream. So before that, we used to have something like that, where you had to use unsafe to initialize like a convar and a mutex, and it was a pain, and it wasn't nice. And now it's just that. Now you can just use PinInit, and there's an interesting syntax there because it's a macro, and it will initialize your mutex on your convar, and it all works. So another trick that we have for Rust is that we have extra lockup checking. So this is an interesting little thing. So how does that work? What we do is that we can set it up so that, for example, every time you create an arc, on the first execution of that line, it will create a new lock class for that arc, for that instance of the, not instance of that call site on the arc. And there's no macros, there's no API changes, there's nothing else. And the magic part is that on every arc drop, lock type engages, so it will do a fake lock. And that way we can discover locking violations that are triggered by, dropping references. So even if you have a drop code path where you're dropping a reference, but it's usually not the last reference to be dropped, you can still check that if that were to be the last reference to be dropped, that you would not be having any locking violations due to running the cleanup code. So that's pretty cool. So the funny thing is how this is implemented is using a Rust feature called track caller, which basically gives you the file, line, and column information of a caller to a given function, and it can propagate across functions. So you don't need any weird magic along the way, any macros or anything like that. The only annoying thing is that, well, it is file, line, column, so we need to map that to a lock class. So there's an ugly open-coded hash table to do that. And, it's locked up. Like, it doesn't have to be perfect or, you wouldn't run it in production. It just has to work and find the locking bugs, and that it does. So the fun thing is that when I enabled this in my driver, I actually found zero bugs related to that. So I think that's another thing that, might not have been talked about Rust, but I think the Rust coding style does actually encourage locking hygiene, so that's pretty cool. But don't worry, it is going to be a mess when we add the fence signaling rules, because right now we are not following, the whole don't allocate on fence signaling paths. We have a few issues there. All that will be cleaned up in due time, and I guarantee there's bugs there and locking issues, so don't worry, it's not perfect, but it works. So, on challenges that we have, we need more reviewers, because, there's a lot of code to review, there's a lot of abstractions, there's a lot of dependencies to upstream, and it is kind of a chicken and egg problem. Because, we have a lot of dependencies, and people want to see the user of the dependencies upstream at the same time, but if it's a giant patch series, that's really hard to review. So, help here is always appreciated and really helpful. The other thing is that chasing unstable Rust features is a little bit painful. So, for example, the latest Rust update broke our device ID table generation because that relied on const traits, which are getting apparently rewritten in upstream Rust. And so for the time being, it's kind of broken, and I'm going to have to figure something out there. So part of it is, just figuring out how to have that, like reduce the number of, unstable features that we use. So coming up, new things for the driver, we're going to be rewriting the page stable management in Rust because that is using IOMMU common code right now, but it turns out that we need too many fancy permissions and too many weird combinations for it to make sense to keep using that. So we're just going to rewrite it inside the driver. And also, I'm going to be integrating the GPU VA manager. I think it's not upstream yet, but it's being reviewed. So that manages all the page tables and address space for mapping BOs, partially and fully and all that. And we need that for Vulkan VM bind support. So that should be really good because the MMU code is like the first part of the driver that I wrote. So it's like the youngest. Not the MMU, like the BO mapping, tracking and all that. So VM bind and DPO VMedge are going to clean that up a lot. And yeah, more upstreaming cycles. So I think it's time to hand off to Alyssa for her side of this whole little adventure.
Oh, wow, we got 4 hats going at once. All right, pretty good. All right, let's get this started. Just magic. I don't actually even need the wand. It just comes through the veins, but it looks better with it, you know? Anyway. So we already talked about the status, but yeah, last year we were kind of working at GLES, I don't know, and this year we're conformance, that's pretty cool, and we're shipping OpenGL 3.1. But actually, we have a branch working with 3.2, and what's the big difference? Well, it's everybody's favorite shader, favorite shader stage that everybody loves to use for absolutely everything. Not that slide. No, let's go forward. Geometry shaders. We all love geometry shaders. Everybody thinks we should just use geometry shaders for absolutely everything. Like if you have a triangle, you know how you should draw that? With a geometry shader. You know why? Because it has geometry. At least that's what game developers seem to think, because they're everywhere. And they're required by GL 3.2, by DX10, I want to say, and by extension, if you want to play DXVK games, VKD3D games, whatever, you need your geometry shaders. And let's talk about geometry shaders. So yeah, real things use them, unfortunately. Like Blender. Blender loves geometry shaders. We have a tepid relationship with Blender. The good news, so I will say off the bat, the Apple M1 does not support geometry shaders in hardware, and it does not support anything even remotely like geometry shaders. I mean, if you look at like an AMD GPU these days, the important part isn't that they literally have a geometry shader stage, it's that they have, you know, the NGG, next generation geometry pipeline, upon which you can efficiently implement geometry shaders. And no, we don't have any of that. We're you know, funny off in Apple land. But the good news is that they are slow everywhere, so they just have to work and it'll be good enough. And we have so much memory bandwidth to waste on the M1 that we should be fine. So, what about mesh shaders? And I'm sure many of you are thinking, well, great, we'll just do geometry on mesh shaders. Bad news, we don't have mesh shaders either in the M1. Womp womp. Apple does advertise mesh on M1, and it's all software. And doing software geometry shaders layered on top of software mesh shaders, layered on top of compute on Vertex, sounds like a way to make your FPS go not stonks. So let's not do that. The Apple M3 will have mesh shaders. I know the M3 hasn't been announced, but don't worry about it. There's telepathic magic, you know? No, the new iPhone has mesh shaders and hardware, so the M3 will too. But the other part is that mesh shaders do not help us with transform feedback. The hard part in all of this is that geometry shaders can emit a dynamic number of vertices and a dynamic number of primitives. They have to declare the maximum amount of data they emit, but they do not have to declare how much exactly they will emit. They can emit fewer than that. So they might say they have a max vertices of 16, you know, maximum 16 output vertices, but they might only emit 3 vertices. So if we layer on top of mesh shaders can do the same thing, so that's fine for emitting geometry. But the problem is transform feedback. Because transform feedback is specified, for those who are uninitiated with another one of our favorite OpenGL features, transform feedback, otherwise known as stream out in Direct3D. So to stream out, the way it works is, the way it's supposed to work anyway, is that the first invocation of the geometry shader writes out all of its outputs to the buffer. And then the next invocation writes everything immediately after that, and so on. So everything is nicely in sequence. The problem is that GPUs are massively parallel, so if you want to implement that, you have to finish the first geometry shader invocation before you can start the second one, which is a complete serial bottleneck, and then your FPS goes not stonks. And the desktop vendors have significant amounts of hardware to sort out this whole mess. AMD, for example, has a very magical ordered append instruction, which is how they implement transform feedback. But the bottom line is that we need to know how many primitives the geometry shader will have written before it runs. So kind of a fun problem there. And layering on top of mesh shaders does not help us. There is a certain competing implementation of a Chronos API on top of Apple hardware that has now opened pull requests for geometry shaders and transform feedback and does not seem to handle the interaction. And they're doing it on top of mesh shaders, but on top of the double emulation, that does not help them with the hard problem of transform feedback. So not really a solution that we care about because we're a conformant driver and we're playing with the big kids. So what's the idea? Well, the idea is that we can run the vertex and geometry shaders as compute shaders or as vertex shaders if you want, doesn't really matter. So the geometry shader, we compile into a compute shader that will run once per input primitive as it's supposed to. It will write out its outputs into some buffer we allocate. It will generate an index buffer, so we can specify that whatever the primitive topology is and whatever the primitive we want is. And finally, it will generate an indirect draw. So all of the vertices and geometry we generate on the compute shader, we feed back into the 3D pipeline with an indirect draw. So far, so good. And then we just draw with a very simple vertex shader, which just reads from our geometry buffer and copies it directly into the 3D hardware. Fine. Pretty terrible. FPS go not stonks, but it'll work, maybe, sort of. The problem here is, again, we don't know where to write. And particularly when we have transform feedback, we need to write immediately after everything previously. So we need to know, so invocation n needs to know how many primitives were written by everything from 1 through n-1. So what are our options here? Option 1 is we cry and run everything in a single threaded shader and FPS goes not stonks. Option 2 is we are wrong and we fail conformance, something that, there's a particular emulator that just did a macOS port and that's their solution. It's just broken, but it's fine. Don't worry about it. They don't have to pass CTS. It's fine. We have to pass CTS. So what do? We could strip down the geometry shader to just figure out how many vertices it writes or how many primitives it writes, and we could run that in a loop at the beginning, but then we still have n-squared invocations over the whole, O(n)² invocations over the whole program, and that's not good. So no matter what we do, we can't do this in one pass and get it right and get it efficient. So what's the solution? We are going to introduce a geometry count shader. So the count shader is a geometry shader that does not write any varyings, any vertex outputs, anything. All it writes is the number of vertices and the number of primitives that it would have outputted if you ran the real geometry shader. So this is pretty easy to do in the driver. We take the geometry shader and we delete everything but the stores. We delete all of the stores and we just keep the set vertex and primitive count at the very end. And then we let dead code elimination go to town. And usually it deletes the whole shader. Or there's a little bit of control flow. We get something very small, and this is the count shader. So we run this, and then we sum them all up into this count buffer. And so now we can read in constant time for any invocation how many vertices and primitives came before it. So it's a multi-pass approach now. We have basically 3 compute dispatches we need instead of just 1. But here's the good news. The count shader, every geometry count shader is running in parallel for all the primitives, so we get good use of the hardware. The geometry shader itself, everything is running in parallel. We get good use of the hardware. So these are both working the way they want them to. So the only question is, how do we do it? How do we do this count? Because it seems like adding up all the things before it, that's inherently serial. Great news, it's not. This is known as a prefix sum, and it is one of the most classic problems in parallel programming. How do you do a prefix sum on a parallel processor? It turns out there are efficient implementations. There's a really great single pass one. It is broken on the M1 because of hardware issues, but it doesn't really matter. At minimum, you can use subgroup ops to accelerate things. So in theory, at least in theory, we have a fully parallel thing, another fully parallel thing, and one more fully parallel thing, and so we got rid of our serial bottleneck. And then we can just implement transform feedback correctly, and yeah. So And just for the record, this code works. It passes CTS. It will ship probably in the next few months or weeks or something. And yeah, let's talk about keeping this clean, because this is a mess. We do not want to write this all in NurBuilder. This is thousands of lines of code, and you do not want this in NurBuilder, which is effectively writing assembly with C macros. Everybody's favorite thing to do. Definitely the right way to program. No, let's just write C. We can just write C, and but compile the C for the GPU, like we're writing a shader. And then we can have a little bit of magic code, which is our specialty here at Asahi. And our magic code will automatically generate bindings for our C code running on the GPU to NurBuilder. And this is a fully generic piece of code, which I am hoping I can nerd snipe every other driver into using, because it is phenomenal and is a massive time saver. And yeah, so let's look at what this looks like. I think it's the next slide. So this is a bit of C code. This is libagx end primitive. So this is the guts of the implementation of the end primitive function in a geometry shader. And so it takes in a bunch of parameters that we calculate in the compiler side, and it does a little bit of math, and it writes out the index buffer, because the end primitive is supposed to fill out a bunch of indices for generating a triangle strip, and then it ends the strip, and that's just an index buffer with primitive restart. So we just write out the primitive, and we do the primitive restart. Detail's not important. What's important is that this is a single screen full of code, and just doing a single for loop in NurBuilder is about a screen full of code. So big improvement there. And on the compiler side, it is completely seamless. Our libagx end primitive function is now a libagx end primitive function, but now it's on the CPU instead, and we call it from the compiler. We did not write a single line of bindings here. It was all automatically generated by Spurvy at build time. So a pretty big improvement. And yeah, so that's the idea, but talk is cheap. Show me the results. Hey, Lina, open Blender, if you can. I think you can hear me.
Fast? All right, let's just give Blender a shot. Let's see if that works.
And this is used, and Blender makes heavy use of geometry shaders, working full speed on the M1.
Yes. So we can do that. We can use this if that is geometry shaders.
And
It works.
thank you. Also,
what was it?
Also, I'm sorry. No, mostly I'm sorry.
Which one
Yeah,
is the
mostly that
downside?
one. Yeah. Anyway, so that's geometry shaders, and I hope I haven't scarred you too much, because next year we will be talking about tessellation shaders. Just kidding. Well, maybe. Probably not. There's a reason I just built a C compiler for the whole stack. Anyway, thumbs up. Any questions now that you've seen the inside of this nonsense? Yes, Friedrich.
So when you as well, when will there be ray tracing?
Hey, you want to work for our team?
I mean, I guess I won't do the entire ray tracing thing, but if you need help with one specific thing, you can always ask.
That's how it always starts, yeah. I just wanted to give Marcan help with one little thing with the getting some pointers on getting started with Mesa, and now I've just implemented geometry shaders in software, so be careful with one little thing. My advice.
Thank you.
What happens if the number of primitives emitted is the result of an atomic operation in the geometry shader that might be different on the second execution?
We cry. So currently, we're not exposing vertex pipeline stores and atomics because it's optional in GLES, and I didn't want to think about that because it makes my head hurt. The longer answer is that at least the Vulkan spec is very unclear on what happens in this scenario, because it says that you can execute geometry shaders multiple times, or at least it's implied that you can. And if so, my interpretation is that putting 2 and 2 together, if you do that, you're invoking, the app has done an undefined behavior, and it's not my problem anymore. I may be wrong.
I'm not sure that's actually quite correct because I think each individual invocation still has to work, and by splitting it in two, and you're kind of breaking that. But yeah, I don't think apps are actually going to hit that very likely. But I
guess my interpretation of the spec, which I chose after I came up with this plan, as one always does, is the spec says that the implementation can invoke these shaders multiple times, and if the app is because of that, all bets are off if you have different behavior in each time it's invoked. And the whole reason why we have that clause in the spec is so apps don't expect their atomic add to do the right thing in a geometry shader. And I don't know. I will be very sad if the alternative is just to start serializing things or start copying things like crazy. And unless there's a CTS case that tests this and an app that tests this, I will choose my version of the spec. Thanks very much.
So obviously transform feedback has a lot of deserialization concerns, but also like normal draws, you have very similar things because like draws in order have to override. And I was wondering, do you use the same mechanism there? And if you do, like how do you figure out how large your buffers have to be, like where you store your geometry shader outputs?
Oh boy. Well, first of all, in terms of where we actually write in the buffer, the index buffer we're doing is fully packed. The generate index buffer is fully packed using the exact same prefix sum infrastructure. This could be optimized, but I had to type all that code for transform feedback. Might as well use it for this. But for allocations, right now, we hope for the best. As soon as you start using geometry or tessellation, we allocate a big buffer, and we just have a watermark? No. The name is slipping me. I did not get enough sleep last night, but we just allocate directly from the buffer on the GPU. And if you run out of memory, sucks for you. I'll deal with that when we get there. There are ways to do much better in terms of the memory usage. At some point, this is sort of unavoidable. The real problem here, what I really want is dynamic memory allocation from the GPU. If this were Mali, Panfrost would support that, and we can do that. As it turns out, doing dynamic memory allocation from the GPU completely violates all of the DMA fence locking rules, which Lina will not want to talk about, I'm sure, because we're all scarred from this. Lina, Faith, Saima, and I had a meeting a few months ago where we tried to figure out how to do geometry shaders with dynamic memory allocation. And no, the answer is, as soon as you start doing dynamic memory allocation, you're going to get deadlocks. Also, Panfrost is definitely broken in the kernel, sorry. So no, we're eating it now, as the kids would say. I'm the kids.
Apple does do that. I don't know how they handle their locking and their rules, but they actually do allocate in the kernel from a callback from the GPU. And we were thinking we could try to implement that, but yeah.
I see no hands, which means you're all sufficiently scared of what has just transpired. She's a witch, burn her! I earned my black magic designation. All right, well, that's the wrap. Thank you. Yeah!
y lo sabe. over, so we put our hands up like the ceiling can hold us, like the ceiling can hold us. Here we go back, this is a moment, tonight is the night. We fight till it's over, so we put our hands up like the ceiling can hold us, like the ceiling can hold us. Here so much joy.
Let there be love, love between brothers and sisters, love between nations and nations. When we get together, we'll have peace and joy. We'll have understanding of one another, united as one. Right now you should be feeling the freedom of this music. Right now you should be feeling the vibe of this song. Everybody should be jumping up and down. Right now
meet you in the summer.
null point for quick 2, or edge flags, provoking vertex mode, and other features. And one of the things that I've been doing for a while now is Uber shaders to reduce stutters. So the problem we're facing is, in OpenGL, there are a lot of ancient legacy features that are controlled by state. So for example, things you said, well, GL set something, and that something affects some feature that doesn't exist anymore in hardware, or just Vulkan doesn't expose, that you normally do with shaders in Vulkan. And so, like nowadays, those things will be done in shaders. So Zink has to emulate those features with shaders. So the problem is state can change at any point. We can't predict how it will change. And this means that when we draw, we might have to compile a shader variant to deal with that particular combination of states, that particular state at that point in time. And because we only know, we can only be sure about the state when we are drawing, we have to do this right before drawing, and therefore we get stutters. So we would like to compile those shaders ahead of time. The problem is, as long as we use variants, that is different shaders for different cases, the number of shaders we need is pretty huge. And another thing that's pretty bad about OpenGL is that all those features can work together with like user shaders. The shader the user can send its own shaders, and those legacy features need to work on top. So this means for every shader the user sends, we will have to compile a number of variants. This makes the problem a lot harder. So Zink so far has precompiled base variants, which works great when the application doesn't use any of those legacy features and there's no emulation needed, but otherwise there's absolutely nothing. So to improve this, Uber shaders could be a solution. So the idea behind the Uber shader is that we have a big shader that can do things that would normally be done by more than one shader that would be smaller, and we have a way of dynamically controlling this big shader, which means this one shader can deal with multiple states by sending the appropriate arguments to it, the appropriate data. So the advantage is we don't need variants because this one shader deals everything, so we can precompile it. The disadvantage is that it can be slower. So this shader, because it has to deal with different cases, is going to have branching, and also it's going to be bigger, and therefore it's going to have more register pressure. The occupancy is going to be lower. Also, it takes longer to process and compile, and this is not something we can fix. But to get the kind of best of both worlds, what we do is we compile the Uber shader as soon as we can. So as soon as we get a shader from Gallium, we just start compiling using util_q. So Mesa is a very useful set of utility functions that basically deal with a queue of work and worker threads for it. So when we draw, if we start by using the Uber shader, so because we don't have any variants for that particular state, so we don't start. We never wait for shaders to be ready. We always draw without starting with the Uber shaders. But when we do that, we kick the compilation for a variant for that particular state. And so next time we draw, the first thing we do is we check if the variant for that state is ready, and if it is, we switch to that variant. So eventually, we don't use the Uber shader. The idea is the Uber shader is going to be used for a few frames instead of stuttering, but then we go to the variants, to the optimized variants that perform just as well. So we get the best of both worlds. We get performance and stutter free. So in practice, there are many challenges to overcome. So first of all, as I said before, we don't have the luxury of just creating shaders. We are not just dealing with the fixed function pipeline here. We're dealing with all of GL. GL mixes programmable shaders with programmable stages with non-programmable stages that are configurable. So it's really about passes. The emulation is done by passes that add the emulation to the user shaders, which means the Uber shader is really a Uber shader pass. It's basically the user shader would do a bunch of passes on it that would be done that normally would be done based on the state, but we do all of them unconditional in this case to get an Uber shader. But we need to control it dynamically, as I said before. For this, sysvols are great. Sysvols are just intrinsics that load a particular value, and we can lower them to whatever we want. So for the Uber shader, we lower them to push custom slows. For optimized variants, they're just we just align the value if we can. Or sometimes you can also use push contents for variants to reduce the number of variants we need. So we need to change the existing near passes to make sure that, first of all parameters they need are passed using sysvols and not for any other mechanisms. So, for example, Gallium has state tokens. Those are not usable for us. We need sysvols. Also, all passes need a way of being dynamically disabled. And this is because we're doing all of the passes, but some features need to be disabled sometimes. And sometimes this is implicit. For example, for alpha test, we can just set the test to always and does nothing. But in some cases, we need to change the pass to add some conditional inside it. In some cases, that's not enough, and we need to rewrite it. And an example of that is near lower flat shade. So it's a very simple near pass that just changes some attributes and some variables to achieve flat shading. But this can be changed dynamically. So the solution that I have consists of duplicating variables that need to be flat shaded and having different attributes in the copies, so that we can then BC cell between them in the fragment shader. This is where it gets funny because, so there are rules about interface matching, and they're such that you can't really predict what the fragment shader will look like. Like you can't predict which slots it's gonna read, because there are some slots that are not passed through, some that are. So in order to deal with this, the way I'm doing it right now, I'm just taking every slot and assigning it to slot times 2, and then the odd slots are free, so I can add my own variables. The obvious problem is called the hybrid shader slots, but we don't have infinite rooms in this case. We can run out of slots. So this is a temporary solution, and really we do that with a Vulkan extension. There is a Vulkan extension that exposes all of the attributes and various handtricks. So we could do the interpolation ourselves or not do it for flash shading. It's not clear to me whether this spec says it has stable vertex order. I know for a fact that some implementations don't. And it's not widely available, so Radvi only implements it starting from RDNA, I think. So this is a bit of an open problem. Another problem is called near pass-through GS. This is a geometry shader that, as the name implies, is supposed to act like a pass-through, which is surprisingly hard, because when you enable geometry shaders, a bunch of features just don't work anymore. You need to emulate them. Also, there are other geometry shaders that are used for emulating quads, for example, and there are also passes done on geometry shaders. So the problem is this pass-through GS is created on demand. Whenever it's needed, it gets bound. This kind of messes with Zink's logic for GPL. So all of this all of the overshaded work works using GPL, because we basically compile all of the shader stages separately from other state. But because when pass-through GS GPL doesn't work, it means Uber shaders don't work. So this is a pretty big deal for us. This is not something I have a solution to for now. So now I'm going to talk a little bit about actually implementing this into Zink. So shader caching in Zink is very simple. As you can see, here's a diagram of it. It's really not. I'm going to try to break it down. So shaders gets created and bound. Shader state gets created and bound by Gallium. And at drawtime, we need to start by looking for a pipeline. So we kind of go backwards. Usually you start from shaders. You have to do lowering passes. Then you have to translate into SPIRV. Then you create shader modules. Then you create GPL. Then you create full pipelines. But basically, the way Zink works is when we draw, we kind of go backwards. So we start by searching for a pipeline. Pipeline are hashed by the state hash. The state, all of the state of OpenGL is hashed incrementally. And so each time we draw, we can just look up a pipeline for that state. And when we find a pipeline, it doesn't end there, because pipelines are at first fast linked and then optimized linked asynchronously. So we must check if the asynchronous compilation is done. But when we don't find the pipeline, that's where we go backwards in the pipeline, backwards in the process. So we need to create a pipeline from the current program. We have to take the GPL for that for those programs, plus some state, of course. So programs are again fetched from cache, and the key in this case is the hash of the user shaders. When Gallium sends shaders, we hash them, and we combine the hashes into one, and we get a key for that particular set of shaders, and that's what caches the program. So to handle variant, the way Zink works is the same Zink program gets this thing called Zink program that more or less corresponds to the GL program, but not quite. And when we need a variant, we update the modules on it, And obviously, we need a new pipeline library for that combination of modules. So there's also a pipeline library cache. The caches might actually be filled asynchronously. So this is how precompilation actually works, by filling caches asynchronously. During steady state creation, we kick the compilation for the pipeline cache. And we add an entry to the cache synchronously from the same thread, so we don't need any locking. But the actual entry contains offense. The idea is the worker thread is going to work on that entry of the cache, is going to do all the processing that's required, and it's going to signal offense when it's done. And the idea is when we need a shader, we can either check the fence or wait on the fence and use it. It gets a bit funny because OpenGL actually allows to share programs between contexts. And the reason you might want to do this is in OpenGL, context can only be accessed by one thread. So for example, Doom 2016 uses a separate context to compile programs, which are then used by the main context. So to support this in Zink, what we have is basically a cache for the cache. When we create a program, instead of just creating a cache for GPL, there's a global cache that gets queried. So this makes sure that programs created from the same shaders end up containing the same cache. So we need to introduce Uber shaders into all of this. So this is no particular trivial. So there's also the case of separate programs that we need, separate shaders that we need to handle in Zink. Basically, in Zink, when separate shaders are used, GPL is created for each shader and then linked together. But this pipeline is then replaced in turn. And what happens is the program that was compiled from the separate shaders gets lost. So this didn't work for me. So I kind of changed a bit the logic to keep so that I could keep the Uber shader around in some structure. So I changed it so that we now have a program for each variant. A program now doesn't need a GPL cache. It only has one GPL because it handles one combination of shaders. It handles one variant basically, and for the cross-context cache, we only need one GPL, which would contain the Uber shader GPL. And now, in order to deal with variant cache, we now have a cache of programs. So for each variant, we have a program in a cache. But we also have a fast variant for the base variant, a fast path for the base variant. The idea is we don't want to do cache lookups to get the base variant, because now the program that gets bound is always the Uber shader. Sometimes we compile the base variant, we need to bind that, which is because it would be more optimized. But also, because this is going to be a very common case, this is actually a special path. And so the logic in general is if we cache hit, so the idea is if we look for a variant and we find it, we need to check if the fence is signaled, because it might actually not be done compiling. If it's not signaled, then we can fall back to the Uber shader. If it is signaled, we can use the variant. But if we miss the cache, it means we haven't even started compiling a variant. So that's when we kick compilation for the variant. So this means that the draw starts compiling a variant, but asynchronously. It only kicks the job. This is actually more complex in practice, because compiling a variant actually requires a few steps. First of all, if the program was created from separate shaders, we need to replace it. So we need to wait for that to happen, which means we delay by, say, 1 frame or 1 draw call. So then we need to run the compilation pipeline. So do all of the lowering passes for that state, and do spreaf to nerve and get the spreaf code, pass it to Vulkan, get the shader module. Then we need to create a GPL for the set of shaders. So the way this is done is each of the stages is synchronous. So the idea is each time we draw and we request a particular variant, we check where we are in this kind of pipeline. So we go through them, we check the fences. When we encounter a fence we haven't signaled, we kick the job for that particular stage. And in the end, when all fences are signaled, means we've done all the steps. We can use the variant. So in the current state, the Uber shader supports the following features. So gel clamp, clip planes, fragment color clamped. Alpha test and flash shade, which I talked about, is work in progress. I'm probably not going to merge it at first. So when I worked on this, I started by not really caring about upstreaming it. So I had like 80 commits. It was kind of messed up. but now there's a merge request which has about 60 commits, so it's not the full patch, but it's what I want to merge at first. So I want to merge what I've already worked on cleaning, and then after that I can go back to the other branch and merge more stuff gradually. So in order to use supershaders, there are some requirements. So first of all, we need GPL. So all the stuff that's required in Zink for the optimal path. Zink basically has this big divide between optimal path and non-optimal path based on feature set. We need the optimal path, so GPL, dynamic state, and other stuff. We also need 256 bytes of push constants. The reason is because in order to emulate GL clamp, we need to send sampler state to the shader, which is pretty big. And actually, I'm still not dealing with bindless textures, so that's not a problem. So I want to give some numbers of this patch. There's a pathological example. There's a trace used in the MSSCI, which is from OpenMW, which is like an open source recreation of Morrowind. And there's a point in that trace where a bunch of shaders get sent, and this causes stutter on pretty much any driver, but it's particularly bad on Zink, because each time a new shader is seen, Zink has to also compile the variant for it if that's required, meaning a shader might get compiled a number of times synchronously. So that's, you get like, without this cache, you could get like up to 193 milliseconds of stutter in that trace. So that's pretty terrible. With our own cache, we get 262 milliseconds. Now with the patches that I've made, at first I got 276 milliseconds with our not cache, which is just not an improvement. So what's going on? Well, the shader cannot handle anything, and in particular, there is some emulation that's usually done by the state tracker, and there's some emulation that's done by Zink. I'm dealing with some of the emulation that would be done by the state tracker, but I'm not dealing with any emulation done by Zink. So when any emulation is done by Zink, the shader wouldn't be usable because it wouldn't produce correct results because it's not emulating those features. So even if a single feature is not supported by the shader, you get a stutter. And plus we get some overhead because, as I said before, shader is actually slower to compile. So that's why it's actually a bit of a regression. So eventually we would like to support all features on shader, meaning we can always use it. But for now, just for benchmarking, we're going to use it anyway. We're going to get broken rendering, but at least we can get some numbers. In this case, I've disabled this cache from Zink entirely. We go from 288 milliseconds to 317 without this cache, and with this cache, we go from 262 to 221. So it's a small improvement. And I've actually rebased this patch recently, and apparently Zink has actually kind of regressed in a way. So now, even without the ACK that I mentioned, so even without using the shader in all cases, we still get 50 milliseconds improvement. And with the ACK, we get pretty much 200 milliseconds of improvement. Again, we still stutter because this game is just sending shaders. We'll never, we'll learn no stutter. Even Radeon SI, you get like 70 milliseconds of stutter. But again, this is a big improvement from not having this patch. So currently, one of the things I'm working on is only starting compiling Uber shaders once they're needed at least once. The idea being if an application never uses any legacy features, we don't want to pay the price for compiling Uber shaders. So we start by using the old logic of pre-compiling base variants, and then as soon as we need the Uber shader once, we start compiling those. This is actually very hard to do. We might end up with some programs that have Uber shader and some that have a legacy shader. So what do you do when you need a legacy feature for those programs? Do you stutter or do you compile Uber shaders asynchronously? It's very, it's a lot to work out there. So I have some implementation of it, but there are a lot of details that I need to work out. So now I want to talk a bit about visualizing them, visualizing user shader in action. So a simple idea is just outputting red whenever we use the Uber shader. But this doesn't really work in practice because objects almost always would be colored or off screen. The idea is the game is not going to render stuff. It's not going to do perfect culling. So you're going to, very often objects are rendering outside of the screen or cold. So by the time you actually see them, the Uber shader has already been replaced, so you don't see it at all. So what I came up with is this very simple pass that just calls discard on half of the pixels in a checkerboard pattern. And this way we can see through those pixels. So the idea is, on the Uber shader, we draw all pixels on a fixed color, which in this case is red, and on the regular variants, we discard half of the pixels. This way, if something is occluding an object drawn by the Uber shader, half of the pixels will basically just come through. So doing that means those pixels would never be written and cleared, though. So also alternate the pattern to make it disappear eventually. That is, eventually, without alternating patterns, eventually the entire buffer becomes red. Not the entire buffer, but like half of the pixels become red. You can't see anything. So by alternating patterns, I can more or less clear the buffer easily. So this is just debugging shader. So it can look like this because it also means that the previous frame kind of survives. The idea being, because I'm alternating patterns, if no Uber shaders are used, you're going to get a little bit of the previous frame and a little bit of the current frame. So it looks very broken. Because yes, I have a demo. You're going to see very broken stuff because you get those images in the swap chain that basically have half of the pixels that are older than they should be. So you get a bit of flickering, and but what you have to look for is red flashes. So every time you see a red flash, that's the Uber shader in action. So for this time, I used Poro, and right away you can see the whole screen is red when I started, and this is the case with pretty much any game because, as I said before, right now the Uber shader gets used for every object at first. For every draw call at first, because we don't have the logic to avoid compiling it. So the first thing you see is a red flash. And if I start going in game, you can see some objects flashing red. So those are being rendered with the Uber shader for those frames. And you can see coming through, as I said. If you pay attention to the portal, first it will be red. Because again, at first you use the Uber shader. There's actually something very interesting that happens here. I'm going to explain it in some slides later. Okay, so I'm going to go back to the slides now. So first of all, this is something you saw. This trick that I did with the checkerboard pattern was to be able to see draw calls done with the Uber shader through other objects. And as you can see, this is working. We can see Uber shader here. This is the portal that I talked about before. So now this is something interesting. You see this laser at first gets rendered with Uber shader. Again, because everything is at first. But later, you see it again. And the reason is those reflections are being done using user clip planes. And user clip planes are one of the features we need to emulate. And so this laser is being rendered again with user clip planes. This is an example where you compile a shader, but suddenly you need to introduce emulation in it. You'd have to stutter, but in this case, we can just fall back to the Uber shader again. So this is why it appears red, as a red quad, because we're falling back to the Uber shader toward the starter. So that's it. We can go to Q&A.
So with this visualization, what is the kind of improvement that you're hoping to make based on it?
So you mean like what's the best that you could get in theory?
No, so we can visualize now like, hey, when do we use an Uber shader versus not with this visualization, right? So like, are there any problems you foresee us being able to solve with that visualization?
Right, so the visualization is very flawed. Like there's, so you can't see where it's the first. Like you mean where you can't see where it's the first time, where we actually need Uber shader for emulation or not. So I didn't understand what.
So like we can see where the Uber shader is used right now. So like, is the goal here to see like, hey, can we see where it's used now, and we're trying to bring down where we're using the Uber shader, like using, for example, heuristics, or like what's the next step here?
Right, so sorry, I'm not managing to. I don't know. I didn't understand the question. Sorry.
So, like we have the Uber. We can visualize the Uber shaders.
Yes.
What are we going to do with that?
No, this is just for debugging. I just brought it here to show it.
Okay.
No, yeah, of course, this is not in the merge request. This is not not gonna find this. What you see if I didn't do this hack, you just see the game running normally. You wouldn't really see the difference. I made this this pass just for the demo to see this is like what is this doing under the hood, right? So the idea is, where you would see a red flash, that would be a stutter normally, right? That's the idea of the demo. It's kind of what it's trying to show. When you see the Uber shader, it means there's one less shader that's being compiled there. That's the point of the visualization, right? I made it for debugging.
So just to try to chime in a little bit, I think that if you want to try to find out how to improve your applications to avoid this, a better approach for that would probably be to add some counters for whenever we're compiling variants or something like that, so that your application can kind of keep that under control. Alyssa just showed me the stop doing Zink meme.
Okay, can I go?
Hello, everyone. You guys hear me? Hello, everyone. My name is Arthur Grillo, and today I'm going to talk about the status of KUnit tests on the DRM subsystem. Little disclaimer, at first, a colleague of mine was supposed to be here with me talking, Carlos, but due to personal reasons, unfortunately, he could not be here. Okay. First, a little bit about me. I was a Google Summer of Code participant this year for X.Org. That's why I'm here. And also I study computer science on the University of São Paulo. I would like to thank the X.Org Foundation, Google Summer of Code, my mentors, André Almeida, Maria Canal, and Thales, and the University of São Paulo. Now let's start with a little bit of context. What is unit testing? Basically, unit testing is when you test individually small parts of your code. Normally, you test functions. So you pass some arguments to that function and see what it returns, if it returns what you expect. The idea is pretty simple, but it can be very, very powerful because first, you can assert behavior, so you know that the function is doing what you think is doing. Also, if some bug occurs, it may fail a test, so you narrow the search area, you know that it's related with the function. And also, if someone sends you a patch, if your source code with the patch starts failing some tests, you know that there is something wrong with this patch. So it's really good for automating and managing source code. So it would be really great to have that on the kernel. And we have KUnit. KUnit it's a unit test framework introduced in 2019 and is maintained by Brandon Higgins and David Goh. It is inspired by other popular unit test frameworks like JUnit from Java, Python's mocking library, and also Google Tests and Google Mock from C++. It has some really nice features like assert and expect macros, parameterized test, that is test that you have one test function with different parameters, so have many test cases with just one test function. It's really great for abstracting tests. Also, some really quality of life features. It can do memory management for you, so if you allocate something inside the test, it can free for you. And also, each test is run inside a try-catch. This try-catch is implemented inside KUnit, so it's really interesting to see the source code. I did. And so it's done like that to see if some error occurs and you assert it. It will reset the context and will not affect the other tests. Now I'm going to explain a little example using KUnit. This is the simplest test that you could write. You just create a function. This function has to receive the KUnit constant as an argument. And in there, you can use the expect and assert macros however you like. Here we're testing if 1 + 1 is 2. I think that is true. I don't know. And this is a parameterized test. First, we declare a struct with how the parameters will be. This we just have an int. And after that, we create an array with the values of those parameters in each test case. After that, you do some boilerplate to make KUnit know that you have these cases and how to print them the name of the test, each case. After that, you have the test function. It's really like the other one. The only difference is that you take the parameters from the KUnit context, and after that, you use the expect and assert macros like you use in the other test. After that, you place those two functions on a KUnit case, and this KUnit case and a KUnit suite, and it's the end. You wrote some tests, some simple tests. So after that, you want to run those tests. So you run in KUnit. You have two ways to run it. You have the KUnit tool. It's a Python script that builds the kernel and runs the kernel for you. If you don't pass any architecture arguments, it will run the UML architecture. So it will run like any other user space program. But if you pass an architecture to him, like x86, ARM, PowerPC, it will run a KeyMove VM for you too. Or if you want to run natively, you just enable some configs and it will run at boot. Or if you enable as modular, it will run the tests when you start them. This is the output of the KUnit tool. You see that this is the output of the example. You can see that our test passed, so 1 + 1 is 2. And another great tool to have when you're doing unit testing on a kernel is GCOV. GCOV is a covering test tool. It's really good to have a sense of how much your source code is tested, and it does that by watching what lines of code are ran when you run your tests. It's really great to have you have 60% of your code coverage, but it doesn't necessarily mean that you have good tests, because you just have to execute some lines. So you have to still pay attention of your quality of your code. This is how you run it with GCOV. You just pass additional configs to the kernel to enable GCOV. And after that, use lcov to collect the files that GCOV generates. And after that, use genTML to generate a HTML file that you can see the cover status. You can see they highlighted the version of GC because there is a bug that you can't only run GCOV with a GC version older than 7, because after that there is some bugs, 2 bugs I think, in GC that impossibilitates the use in the kernel. This is a no issue, and it was already discussed, but it haven't seen a fix because it's too difficult, because you have to change a lot of things in the kernel and in GC too. All that I learned from this blog post, so if you want to know more, please go there. This is an output of GCOV, and in fact, this is the output of the core functions of DRM. As you can see, we have a lot of reds, so we still have a lot of work to do, and that's what's the theme of this talk. But let's see what we have. We have some of the core files of DRM tested, not all of them. You can see some of with better coverage here on the first image. Also, we have on the TTM, one of the memory managers of DRM, and also the VC4, the video driver for the Raspberry. You can see the coverage from TTM on the second image. But I think we can do a lot more, like we have on the test on TTM, why you can't have it on Gem, the other memory manager. Also, when I sent a patch to VKMS, another thing, there was some discussion about adding unit tests to VKMS too, another driver of DRM. So we have a lot of places to add tests. We just have to do it. So we have a lot of work to do. This is what I did. I wrote some functions to the DRM rect and some tests, the test for the functions from DRM rect and DRM format helper. The DRM rect is just some functions that operate on the DRM rect struct from DRM. And the format helper is some functions that convert from one format color to another. The first file was a little easier because it's just some math operations, so it's a little easier. But the format helper was a little more difficult. As you can see, I didn't got it 100% of coverage because some functions needed some mocking to do because it uses I/O, and due to time, I couldn't do it. But in the end, it was still a pretty good work. We got 94% coverage, and it's on the kernel now. Also, another aspect of KUnit is that I think it's a good introduction to new developers on the kernel. Because first, we have a lot of work to do, as I demonstrated. But also, the most things that I struggled when I was developing to open source, but specifically on the kernel, when I was first starting, was that I found a lot of things to do, but few of those things I think I could do, because I didn't have the knowledge to take a task like fix this thing or add this feature, and subdivided in smaller tasks and go and work on them. But unit testing is it's already a small task. So it's really good for new developers to start doing that. Also, another aspect is that when you are unit testing a subsystem, you are gaining knowledge about the subsystem. You have to know what the function does and why this function exists. So it's really good for creating knowledge from a subsystem, so the developer could do other tasks on the subsystem. This is a case of study that this was a test function that I wrote. It was I think the most complex one that I wrote. This tests a function that main copies some data from one frame buffer to another. It basically does that, but it was complex because it is one of the few functions from the RAM format helper that support color formats that have more than one plane, and so it didn't exist any other test that had this support. So I had to write it. And to know about color formats, that color format can have more planes, and how the memory displayed on the RAM, of that I need to learn and about subsystem. So it was a great way to learn about subsystem. Also, I had some complex issues with the type of the array, because some color formats have each channel doesn't align the size of each channel. So, and little ending endians, all that stuff, great stuff. But then I got it working. You can see that I have the same case with different formats, and this format has different number of planes. And it was pretty great to do some testing on the kernel. So if you have someone that wants to start kernel developing, I think you can ask him to test some functions that you think it would be good to have some tests. And that was my talk. Some questions?
Hello. Okay. While you were writing the test, did you encounter any bugs that were, did your test uncover bugs?
Unfortunately, no. But it would be really cool to see. But no, I didn't found. It was really great to see like how this function really worked. And sometimes I think I thought that I had the test right, but the function is not passing because I didn't understand how the function was really working. So it was really great to have a good sense of how the function was working. But no, unfortunately no. But we don't know, like, after some time this function has a bug, so the test catch it, so yeah. Oh.
Just for like feedback, I definitely encountered some bugs so I'm the one who did the testing on the VC4 driver.
Oh.
And so, yeah.
Yeah.
I definitely did.
Yeah, so it's really great to have unit testing on the kernel. Really great to know that. So I think it's done. Thank you.
we found love as the leaves turn brown, and we could be together, baby, as long as skies are blue. You act so innocent now, but you lied so soon. When I met you in the summer,
Testing, testing. Sounded like it was on, didn't it? Everyone, thank you all for coming. I'm going to talk to you today about my Google Summer of Code project this summer, which was wlroots frame scheduling. So this summer, I didn't mean to leave that in. This summer, I did useful work on software, and we're going to see everything that I did and everything that I didn't do. And if you are a user, by which I mean a compositor developer, not a Sway user, for example, pay close attention because there are breaking changes. I'm sorry. So we're going to start out with the situation we find ourselves in, which is the same situation as any graphical application is going to be in, where we have a couple of problems to sort of reconcile. Firstly, the display is probably, usually, going to refresh at intervals, say 60 Hertz, and we're not able to influence that. It does it. The real world does not refresh at 60 Hertz. Users can move their mouse, they can press keys, all kinds of things happen, and the users will be angry at you if these mouse movements take too long to get to the screen because they want it to happen in good time. And finally, not finally technically, but rendering, we don't know how long it's going to take before we do it. So that's another kind of spanner in the works. And the real finally, which is not relevant to every graphical app, but it is relevant to compositors. Clients also exist, and we have to get them to render. We tell them to render, and when they finish, we use the things that they give us to put them on the screen. And they're evil. They like to do things like multiple frames per frame, or complaining. They like to claim they're going to render a frame and then not. You can't really trust them. So you've got to take all of these edge cases into account if you're touching this kind of stuff, which is fun. So the state of things at the moment is that most wlroots compositors use this scheme. I think Sway doesn't because it's special, has enough users for someone to care and like make a special case for Sway. But it's encouraged by the API of wlroots that you would have something that looks like this. And specifically, what we have here is that on a refresh from the display, the compositor becomes aware of that and immediately does both things, telling the client to start their rendering and starting its own rendering. And they happen at the same time. And that's not good. We don't want to tell the clients to start rendering and then immediately start rendering ourselves, because that means that the client is guaranteed to not have finished rendering by the time we start. It's not going to happen. And as we can see here, a good way of reasoning about this is that client render 1 is finished before compositor render 2, and compositor render 1 would ideally have picked that frame up, but it can't because it started too early. So ideally it looks like this. And what we want to happen is that our compositor rendering finishes just in time for the display to scan out. And this is true, like I said, of a lot of graphical apps. You'll have some kind of deadline, and you want to finish rendering as close as possible to that deadline, so that you're not sitting around with a frame that you've rendered, unable to do anything until the display refreshes. And here, I didn't change the client render times. They can do what they like, but usually they look something like that. And now we can see that client render 0 is going to finish before compositor render 0, which means that client frame will make it into display refresh 1. And that means you lose 16 milliseconds of latency on a 60 Hertz display because you're displaying those client renders 1 frame earlier than you otherwise would have. So I came into GSoC and I thought, okay, this will be fine. I know what I'm doing. I'm a smart person. And I forgot to click through all of my lines first. So if I backtrack a little bit, then we'll see the compositor render is also able to pick up user inputs. So those 3 far on the left are going to make it into compositor render 0 because it starts after they happen. And they'll make it also into display refresh 1 instead of 2. And like I say, users love to have low latency. They love to move the mouse and then it happens immediately and everything looks smooth. I don't remember screwing up my animations on this one. I checked it many times. But I went into this, I thought, I know what I'm doing. It'll be fine. And I tried to sort of redo wlroots' frame scheduling infrastructure. You can see a screenshot from GitLab right here of my first patch to wlroots on this topic. I sort of, patched up a few things, put a call to this in there, redid how that works, and tried to add the delay between the present notification and the start of rendering. I thought I had it all covered. I absolutely didn't. Kenny came in and said, better worded than that. But he said, that's not it. Things are like that for a reason. Please don't make them break. You are supposed to, in GSoC, learn about the project that you're going to work on just before the summer. But just before the summer is exams. I'm not sure how they missed that one. So I kind of rolled in and became the reviewer's problem. But thank you to all reviewers who are patient and help the authors learn, because this would have been awkward otherwise. So we know that we want to finish rendering as close to the deadline as possible. And if we go over, that's tragic, because then you have to wait for the next refresh to come around, which is even later. And we don't know how long it's going to take to render, but we can guess. So I think strategies that people have already implemented this I think KUnit uses a window of maybe 15 previous frames, and they'll say, so some of them took 3 milliseconds, then one after took 4, so the next one is probably not going to take more than 5. And then they can use that guess with a bit of tolerance built in, because you might guess wrong, to time the start of the render correctly. And in wlroots, we didn't have any way of measuring how long a render pass took before, in fact, at all, before I came along. So that was the first task after the failed flailing around at the beginning, is for me to add a way to measure the duration of render passes, the time from submitting them to when they become available for display. So now, if you're a wlroots user and you want to know how long your frames are taking, you can use this nice interface, which is implemented for Glass 2. Not Pixman, because the answer is going to be like 3 seconds anyway. And Vulkan, I have the implementation on my disk. I need to submit it. I'm sorry. If you're using Vulkan, then you're strange anyway. I think that backend's experimental. So we're back to here. Now we have a timer to learn from. And we want to make good guesses as to how long a frame will take based on the duration of the previous ones. So I thought, being the idiot that I am, it would be cool if we could see the frame time behavior. So I thought I'd develop a visual tool that drew a nice little graph of the frame times, and you can see that when you open Firefox, it went up by 4 milliseconds, so you need to build in tolerance for that. What a great idea. And then people can adjust the parameters in the other work such that we get the tightest possible deadline squishing. But alas, the way I thought would be a good idea to implement this was inspired by seeing GPU Viz, which Simon thankfully recommended to me. You don't need to be able to see much of the detail in this picture, but I do want you to gather that it's clearly a pretty extensive program. It's got 7 blue arrows. How many more blue arrows do you want? And you can see all kinds of data in GPU Viz. You can filter, scrub, you can do all sorts of things. So I thought, if I'm trying to visualize things, it would be a good idea to use a pre-existing tool rather than to build the whole thing from the bottom up. So I thought, well, let's try to inject events, custom events, into this timeline. And it is possible to do. But you have to be a wizard, apparently. I wrote a library to extract over the kernel interface, because GPU Viz extracts its events from Linux, and Linux is able to maintain a timeline of sort of fences being signaled and whatnot. It has this user events data file that you can open and do some OCTLs on. So I wrote a library to abstract over that, make it nicer for people to use. But it didn't go well. I had all kinds of problems with this. Events just kind of wouldn't come through sometimes. Not sure why. It didn't work. I ran out of time. No more frame time tool for us, which is sad. But you can still use the library if you want. If you're doing some injecting of these events, feel free to download it and use it. So with the tracing and the visualization having failed, back onto the main track, I was going to have another stab at redoing the scheduling infrastructure in wlroots to make it not encourage the bad timeline that we saw at the beginning. But that was tricky. The old interface, which is still in master because we're nearly there, I'm sorry, is primarily based around this function, schedule frame. And by calling this function, you're asking, please can a frame event happen at some point? So it's like saying, if the render loop is asleep, wake it up. But otherwise, it's fine. We just carry on. And that turned out to be quite hard to reason about, which was a shame. But after many weeks of thinking and going to bed and thinking while I was in bed and then getting back out of bed and trying to implement that and then thinking I was stupid while I was in bed because it didn't work, I finally came up with something, which is the new frame scheduler interface. And there is currently an open merge request and it's been through a few rounds of review and it's hopefully going to get through soon. But what this does is it gets rid of the old WLR output schedule frame, which is tied into WLR output. And outputs are necessarily keeping track of things that are the frame scheduler's concern. So with the new interface, things can be taken out of WLR output to leave it more tidy. And also, we now have different implementations of the interface based on what use case you're aiming for. So this was already, all these use cases were already supported before, but it was getting kind of messy because, for example, on DRM or on Wayland with WP presentation, you can receive presentation events from the display and then use those to drive your render loop. But if you don't have that Wayland extension, then you have to use wlsurface.frame, and that has different semantics. And then if you're on headless, you have to just invent the whole thing yourself because there's no display. And it was getting a bit hairy with all of these use cases being covered kind of by the same thing. So now we more explicitly have an interface, and you construct one of these objects, and you can attach it into your scene if you're using scene, or you can just use it as it is. And this, I do think it's, along with the timers, one of the two things I actually managed to successfully do in summer, which was fun, because the tracing took many weeks out of my project, because I thought it was going to go well, and I really wanted it to happen, but it didn't. So yeah, this is the biggest part. Render timers are cool, but they didn't take very long. This took a lot of thinking, unfortunately. And I do think it's going to make it in. No pressure to maintainers, but it does look quite promising. Yeah. And one day, with the new interface, I did design it, of course, with this in mind. My original goal was to wait after present before rendering. And that is not implemented by the new interface, but it will be pretty simple to add another implementation of the interface on top of these ones that we already have, that will support, compositors saying, okay, the next frame I think is going to take 6 milliseconds to render, so please wait 10 milliseconds before you start it. Compositors will eventually be able to say that into the scheduler, and then the scheduler will do its magic behind the scenes and have a simple interface like the one before, and will allow us to get these latency wins hopefully without too much churn downstream. But it didn't happen in the GSoC period. I'm still trying to keep it going, but unfortunately university exists and I have to go to it. So in the meantime, I've made breaking changes, which is introducing the new interface and removing the old one, but no latency benefits yet, so I'm sorry about that. Enjoy the render timers though, because no downsides there, it's not breaking anything. Thank you to Simon for putting up with me and my horrible webcam. And thank you everyone for coming. I pray you don't have to see me again. Thank you.
Hello. It sounds like we've solve basically very similar problems in Gamescope as well. So we also use GPU viz in Gamescope. Is there a reason you didn't just use the GPU viz tracing header and try and do it yourself?
So I was hoping to, when I say I was hoping to build my own tool, I did notice in GPU viz there was kind of a glaring standing out problem, which was that you can't see events happening live. And I thought that would be really useful. Like I was saying, if you open Firefox and you see things jump up, you can immediately think, okay, that was the problem. So in GPU viz, you have to record a stream and then play it back by loading it up into the visualizer. But I wanted something that would have this like continuous view of live frame times. So I was using the Linux tracing shared infrastructure in the hope that someone might load it up in GPU viz and still find these events that I was going to remember useful. But I didn't aim directly for GPU viz in the hopes that I would be able to build a custom thing.
Okay, and second question, does wlroots, does it wait for buffer latching on the CPU or the GPU? Because that might have like a big impact on, because you said you were measuring the rendering time, but if you're waiting for buffers to be ready on the GPU, then your render time is basically also completely including all of the client's render time until after it's committed the frame.
So Simon's noticed this and wrote some code. I can't remember if it got merged yet, but not yet. Wrote some code to wait on the CPU. And when I say wait, I don't mean block, but rather if we know that a buffer isn't ready yet, just pretend the client never made the commit, I think is the logic.
Yes.
So yeah, we don't wait on the GPU in the ideal world where all these things have landed. Yeah.
Okay. Oh, sorry. One more. Is there anyone else? Okay. Another question is because wlroots composites a lot of the time, aside from like the direct scan-out case, have you ever thought about doing GPU work might cause a clock feedback loop? Because that's one thing that we had with Gamescope for a decent amount of time, is that whenever we would composite, sometimes, because we're pretty aggressive to targeting VBlank, that eventually we keep pushing forward and forward and forward because the apps, the rendering time takes less and less, and we push forward enough that the GPU cycles down, and then it takes way longer, and then you get a stutter. Have you ever had any thoughts about trying to address that?
So I've definitely had thoughts. I didn't try to address that because it terrifies me. I don't think I know enough about sort of kernel graphics driver APIs to know if they have any way to say don't increase your clocks because of this job or anything like that. And I feel like clocks are going to change whether I like it or not. So my solution was to just ideally make the tolerance built into the weighting big enough such that if problems start happening where renders take longer than expected because of clocking, then the tolerance catches that and there's no problem. If you have a feedback loop where the clock increases, I genuinely have no idea what I can do about that, unfortunately.
So I don't know if Rob is in the room at the moment, but he was working on some stuff in the kernel with it was DMA buff deadlines, I think is what it was called, which is precisely to solve this problem, in particular the problem where you have clock frequencies jumping up and down based off of different stuff. So you might want to consult some of that potentially. I think that's still not upstream yet. Yeah, it's getting the CPU weights involved also kind of makes hash of things, and there's a few other places where it kind of has problems. So point is less that it's solved and more that there are other people working on it, and you should talk to them, and there is some priority.
Yeah, that's good to hear. I hear there were worries about the CPU weighting thing. I wonder if sort of deadline communication is going to be available to clients as well, like any old app that's rendering. But yeah.
The core DMA fence deadline stuff is wired up in the kernel, and it's wired up for KMS atomic commits. What's missing is exposing it to user space, and that's mainly because we were waiting for a user space to use it.
Right.
So it's in that, there's patches that exist, it's kind of in that waiting for an upstream user space use. So yeah, it's sitting there waiting for a compositor to come along.
Right, yeah. So I should have a look at that then. Thank you for pointing that out because I hadn't heard anything like this. Any more questions? Looks like none. Thank you very much.
Let there be love, love between brothers and sisters, love between nations and nations. When we get together, we'll have peace and joy. We'll have understanding of one another, united as one. Right now you should be feeling the freedom of this music. Right now you should be feeling the vibe of this song. Everybody should be jumping up and down. Right now is your time.
All right then. Is the mic live? Test, test. Great. Hi everyone, my name is Friedrich. I work for Valve on Redvi, and welcome to my presentation about Redvi's ray tracing. So we're gonna start right off, if the slides can actually move. Like, do I need to point it somewhere? Ah, there we go. So we're going to start off by just recapping the Vulkan ray tracing API from an application perspective and how it uses it to actually do ray tracing like in your app. And after that, we're going to look at how we implement these same APIs in Redvi. And in both cases, we're just going to start with acceleration structures and then move on to ray tracing pipelines. So first of all, we're going to look at the acceleration structures. And they're basically the main scene container that if you want to trace some rays across a scene, you'll put your scene into that acceleration structure and give it to the driver and tell it to trace some rays. So this whole structure is, of course, dependent on which exact ray acceleration hardware you use. So it's completely opaque from the app's point of view. It doesn't actually know what binary data is encoded inside that acceleration structure. And to actually construct these structures from your average triangle mesh or whatever, you just kind of give all your triangles to the driver and just tell it to, hey, please build this acceleration structure for me. There's also some other primitive types aside from just triangles. You have ABB primitives, which, for example, you can use for procedural geometry. If you have your geometry that's not defined by some amount of triangles, but rather by some equation, you can put in the ABB of this primitive that's going to be defined by the equation, and then you're going to give the driver some piece of code that will calculate whether a given ray intersects with that geometry or not. And that way you can kind of have any sort of intersection function or geometry that you actually want with this ray tracing. Another primitive type is an instance of another BVH. So if you want to have like 2,000 trees in the scene, you don't need to actually build 2,000 different acceleration structures for these trees. You can just build one and copy-paste it into another acceleration structure. And Vulkan sort of enforces this behavior between instancing other BVHs in that it has a top-level acceleration structure where there can only be instances of other BVHs, and these instances can only be bottom-level acceleration structures, and those themselves can only be composed of these triangles or ABBs. So in the end, you always have this top-level acceleration structure, which will refer to some bottom-level acceleration structures containing some triangles. Now, with that in mind, let's trace some rays. We have the ray tracing pipelines, a special type of pipeline specialized for that. So usually you'd have your graphics pipelines for performing rasterization or compute pipelines for performing compute operations. And ray tracing is basically the same thing, but just for ray tracing applications. With that, there comes a new set of shader stages. So before you'd have like vertex shaders, fragment shaders, and compute shaders, and so on. And ray tracing introduces a whole bunch of new shader stages called ray generation, any hit, intersection, closest hit, miss, and callable. And the control flow between these stages is sort of complex. So in a ray tracing pipeline, you just, in a rasterization pipeline, you just go from vertex shader straight to tessellation, geometry, and fragment, and so on. In the ray tracing pipeline, this whole thing is a bit more complex, but you do start with a specific shader, which is called the ray generation shader. That's basically used to set up some cameras, determine from where the ray will start and the direction in which the ray will be traced. And then you'll end up calling trace ray. That jumps execution to a ray traversal function, which is defined inside the driver. And that's where the ray hardware will traverse your acceleration structure and try to find intersections with primitives. If you find an intersection with an ABB primitive, you call the intersection shader, which is responsible for determining, with procedural geometry, determining the intersection points of rays for that equation you set as for the procedural geometry. It can, of course, report that hit to the driver, which will then jump execution to the so-called any hit shader, which can then evaluate that hit if it should actually be considered. For example, if you have some geometry that has an alpha texture and you want to do transparency correctly, you would sample that alpha texture in the any hit shader and reject the hit if it, for example, the transparency is 0, because then you didn't actually want that particular location to show up at all. If you have triangles that are hit, then of course the intersection shader doesn't make any sense, so we just jump directly to the any hit shader. And intersection shaders and any hit shaders can both reject hits in the intersection that's just not reporting any hit. then the execution will just jump back to the rate traversal where it will try to find more intersections that it can pass to intersection or any hit shaders. If you do find an intersection and the any hit shader confirms it, then you'll end up in the closest hit shader. And of course, if you have multiple hits, then you need to choose one. And the one that is chosen is always the one that's closest to the ray origin. That's where the name closest hit shader comes from. And if you don't have any hits that were accepted, either they were none found in the first place or the any hit shader rejected all of them, then you're going to go to the miss shader, which will then just execute some code that you, example, want to set for sky colors or something. And that's what you, for example, would do in that miss shader. There's also another cool thing about ray tracing pipelines in that you can actually do full recursion. That means you can call the trace ray function from the closest hit and miss shader again, and that will jump back to the ray traversal and do the whole traversal loop with intersection and any hit shaders again, and then call more closest hit shader and so on and so on. But there's always a driver-defined limit. So for example, on Redvi, you can't go above 32 levels of this recursion, and there's drivers where you can't even do any recursion at all, so the max recursion level is just 1. Another shader stage I didn't talk about is callable shaders, and they're sort of separate from this whole control flow of the normal ray tracing pipeline, and they can be invoked from any shader that's outside this ray traversal loop. So intersection and any hit shaders can call callables, but ray generation, closest hit, and miss shaders can. Also, callables can themselves recurse again into other callables, so you can call callables from callables and so on. Now, there's all a lot of flexibility, and we have a few other concepts to kind of support that. The first major concept is the shader binding table, where you can have more than one shader for each stage, and to determine which shader is actually called, you store references to these shaders in that shader binding table, and when you call, for example, a closest hit shader, then the driver will look at the closest hit shader binding table to find out which handle of the shader to execute, and then it will jump to the shader that's referenced by that handle. If you're familiar with jump tables, it's basically the same thing, but just on the GPU. And if you have that many shaders, it's also useful to move some common shaders out into a separate compilation if you want to use them in lots of ray tracing pipelines to not have to recompile them again and again for each ray tracing pipeline. And that's what pipeline libraries are there for. You can move these shaders out into a different pipeline library and just reference it from any other ray tracing pipeline that might want to use them. This library concept was later reused for the graphics pipeline library extension, so if you're familiar with that, it's sort of a similar thing, but just for ray tracing pipelines. Now that we've got a rough overview of the API, let's look at how we actually implement this thing, and we'll start with acceleration structures again. So on Redvi, acceleration structures are implemented as so-called bounding volume hierarchies, or BVHs, which are basically just a tree structure made from your triangle or whatever mesh that you gave to the driver. So in that tree structure, each leaf node of that tree will be equivalent to one triangle in your mesh if you have a triangle mesh. The parent nodes of these leaf nodes are then so-called internal AABB nodes, which just aggregate multiple of these triangles into one AABB, and that's basically what the nodes represent. And these internal AABB nodes have some other AABB nodes as their parents, so we just aggregate everything into fewer and fewer AABBs as we go up that tree. And when we reach the root node, then we'll have one AABB that basically encompasses the entire scene. And that's useful for array intersection acceleration because, for example, if you have an array that just goes way outside the scene, then you can immediately reject that array because it likely doesn't even hit the root node's AABB, so you can just test against the root node and immediately say, yeah, that array misses completely, just execute the miss shader. And that also works for like deeper levels where you have like only one child node that actually hits the array and all other child nodes miss, so you can discard all of those child nodes and only look at like the one child node that actually hits. In AMD hardware, we have a so-called BVH4, which just means that each of these internal nodes has 4 other nodes as its child nodes. And I've actually got some structures that actually represent the ray tracing nodes as they're used in Redvi. So for the internal nodes, we refer to each child node as a 32-bit integer pointer, which packs both the ID and type of that node. So we can distinguish whether we are pointing at another internal node or a triangle node or whatever. And this type is packed into the least 3 significant bits, and node offset in that BVH in multiples of 8 is packed into the other bits, which essentially makes the required alignment for these BVH nodes 64 bytes, because the least 6 significant bits are unused. So that's what the 4 other integers at the end of the ABB node are there for, just to have the proper alignment when we have lots of these structures in an array one after each other. For the triangle node, we of course first store each vertex of that triangle to check against. And then we also store some other metadata, like the index of that triangle within the geometry it belongs to, the index of the geometry it belongs to, as well as some other flags for that geometry that influence some things about ray traversal. We also have the ID member, which essentially tells the hardware to reinterpret certain things about that node structure, but we just set it to a hard-coded value for now. Now, building acceleration structures is kind of a multi-step process. We first convert each input primitive to one leaf node, and then we sort all of those leaf nodes, because the app might provide these leaf nodes in some random order, we don't know which, and it's pretty unlikely that that order will be useful at all for BVH building. So we use a concept called Morton codes for sorting. And the cool thing about Morton codes is that they are constructed in such a way that if you have triangles that are close together in space, their Morton codes will also be numerically close. So if you then sort all of your nodes by these Morton codes, you will have nodes that are close together in space also be close together in memory. And that's useful for further BVH building. Then we use some algorithms to construct a binary BVH, and we mostly use the binary BVH at first because all of the research algorithms for BVH building only concern themselves with these binary BVHs. At the last step, we just convert that binary BVH into the BVH4 that's actually used by the hardware. Now, a big disadvantage of having this many steps is that you actually need to synchronize the whole execution in between each step. You can't just start sorting nodes when you don't actually know which nodes you're going to have in the end. So we have to insert pipeline barriers between each of these steps. And if you have lots of tiny acceleration structures that you build one after another, that's going to be terrible for GPU utilization. That's why Vulkan also has a concept of batching multiple acceleration structure builds in one command, and then we can just execute all of these steps in parallel for each of these acceleration structures, which kind of solves that problem. And this batching actually makes a huge difference in practice, because if you don't batch, your thing's going to look like, your GPU utilization graph is going to look like this. And that's basically the worst case you can actually get. Like, you have around 100 milliseconds of frame time, which equates to 10 FPS, and 60 milliseconds of that, so roughly 2/3 of that, is just spent building acceleration structures with really garbage utilization. So it's best to just batch. Now, I'm going to take a quite short look at how we actually implement these binary BVH building algorithms, because we have 2 of them. So the first one is pretty simple. It's the linear BVH algorithm, which is from 2014, and just builds up a radix tree from the generated Morton codes we generated earlier. And the cool thing about this algorithm is it can build up the entire tree completely in parallel, which is great for executing this on a GPU, because you don't need any sort of synchronization in between tree levels or anything. That's why we use it for builds where this whole build process needs to happen really quickly, and we don't actually care that much about how good the BVH is in the end. Like, it's not terrible, but it could also be better. This is, for example, the case for many top-level acceleration structures that just contain all the objects in the scene, because there likely won't be as many objects as there are triangles in the scene, and most of the time the objects move around somehow on each frame, so you need to rebuild that top-level acceleration structure each frame, and having a quicker build algorithm just helps make all these rebuilds faster. The other algorithm we have is parallel locally ordered clustering, or PLOC for short, which is better quality than LBVH, although it's quite a bit slower. This is mostly because it actually needs to synchronize after building each tree level, and we don't know how many tree levels we have to build in advance, so we can't just emit some pipeline barriers and be done with it. We actually need something to trigger a whole GPU-wide synchronization from inside the shader. The original implementation of this algorithm was written in CUDA, which has a special intrinsic for this, so they didn't have that problem. But our build shaders are written in OpenGL, so we have a big problem on our hands. But we solved this by making our own kind of synchronization primitive for this, and that's what I'm going to talk about next. So since our build shaders are written in OpenGL, we don't have many intrinsics we can play with, but we know the target compiler and we know the target hardware, so we can make some extra assumption about this. For example, we can assume certain things about independent forward progress. That is, if we have some invocations that just continuously poll a value in memory and busy wait on that until it changes, that actually won't starve any of the invocations doing actually useful work. So at some point, if the invocations doing useful work aren't starved, that they'll finish and we can exit that busy wait loop and continue on with our work. Another guarantee we can make is about launch ordering. So if we have a compute shader invocation that launches with a certain launch ID, we can assume that invocations with a smaller launch ID have been launched already. So that's basically used in some other places to implement a lighter sync without actually having to synchronize the whole GPU every single time. The thing that we went for the whole GPU synchronization is basically a work stealing queue with unsigned integers as the task IDs, and that's basically just what you refer to for each task. So it has a unique identifier, so you can figure out what to do given that unique task ID. We also needed to have a runtime defined number of tasks to launch before synchronizing, because we also don't know how many nodes there are in each tree level before we actually build the tree level. So we need to know we need to determine how many nodes we have to launch before we actually, just before we launch that shader for building those nodes. So launching new tasks is pretty easy. We just atomic add to some task counter, and that gives us a unique task ID. But actually making sure previous work is finished is a bit more involved. We maintain a finished counter that just keeps track of how many tasks are finished, and we have a maximum task ID. So we keep track of how many of the maximum task ID that needs to finish before we can launch new work. And then we just compare if our current task ID is greater than that. If it is, we need to wait until the task ID gets incremented. And the last invocation to finish its task that would just wait otherwise, that one will update the maximum task ID to launch new waves and free them from this busy wait loop so they can do their work. Now, this was a bit oversimplified. The actual algorithm for this is a tiny bit more complex. But this is pretty much what we use, and it's served us pretty well, actually. We are pretty competitive to the AMD proprietary driver in terms of build times, so this is mostly just what we went with, and it's been doing us pretty good services so far. Now let's talk a bit about how we actually implement the ray tracing pipelines, because that's basically where the second or the biggest changes since XDC 2022 happened. So the hardware actually provides us with some parts that accelerate ray BVH intersection, which is this image BVH intersect ray instructions. And that just calculates the intersection results for a single BVH node. So if you have one internal ABB node that you want to test against, that instruction will go through each of the 4 child nodes, test that against the ABB, and test its ABB against the ray. And then it will give you each of these child nodes that hit the ray is sorted by the intersection distance. So the ABB or the child node that was intersected the closest to the origin will be returned first, and other nodes will be returned later. It has also another mode for triangle intersections where it will return how far the intersection was away from the origin and at which barycentric coordinates inside that triangle the ray actually hit. That's useful for shaders because they do some per vertex parameter interpolation stuff based on that barycentric coordinates. So we also have some new concepts in RDNA 3 that were added there, but RedV doesn't actually use those yet, and I think we're kind of running out of time, so I'm going to skip over those. But that's pretty much all there is for the hardware, and all the rest is implemented in software. So the software implementation has changed quite a bit over the last years. So at XDC 2022, we had basically this kind of implementation where we just inlined everything, the whole ray tracing pipeline, into a single compute shader and refer to all of the shaders by their IDs. So we had like a giant switch case for each of the shaders, and if their ID matched the ID that we wanted to call, we'd execute the code for that shader. And since there's arbitrary recursion and you don't actually know how many shader calls you're going to make, we also had like this while loop, so we continually would call new shaders until the shade ID was set to 0, which would signal that we should exit the shader instead. Now in XDC nowadays we have encountered quite a few problems with this. The biggest problem is just that ray tracing pipelines are really big. Like games create up to 2,000 shaders in a single ray tracing pipeline, and stuffing all that into a single compute shader isn't going to work. We found shaders that were so big, when we executed some recursive compiler passes for them, we just ran out of stack space and crashed completely. So that wasn't really a sustainable approach for bigger compute and ray tracing shaders. So we changed that up a bit today. And another limitation of that approach was that the whole concept of pipeline libraries, where you just compile your shaders or parts of the ray tracing pipeline beforehand, doesn't really work, because you need all of the shaders inlined into singular shaders. So you can't just compile parts of the ray tracing pipeline at one point and other parts at some other points. So nowadays we have two different modes for compilation. The first mode is the monolithic mode, which in many ways is pretty similar to the XDC 2022 mode. But the most stark difference there is that we don't support recursion in this mode. So we can just copy-paste all of the shaders at the sites where they're actually called, instead of having to do this while loop thing. This also allows us to do some constant propagation in some cases. If we, for example, call this trace array function with compile time constant ray flags, any branch that checks for these ray flags can be flattened at compile time, because we already know which code path will be taken. This code path also doesn't support any pipeline libraries, but we might get to that later, depending on how well they fare with the added complexity of just much more shaders in the programs that actually use ray tracing pipelines libraries. So the other mode that we have is the separate compilation mode, where we implement these shader calls with an actual indirect jump. And that allows ray tracing shaders to be completely compiled separately, so we can actually use the pipeline library functionality. But this comes at a cost of being pretty complex, and also we can't just inline every single shader. So the intersection and any hit shaders are still inlined into a single big traversal shader that then encompasses pretty much the entire ray traversal loop. And just the shader calls outside of that I marked in green here, are implemented with actual indirect jumps. So the traversal shader looks something like this. We have the main loop that just fetches a node and executes the hardware instruction for it. And if we see that we need to execute any hit or intersection shaders, we just copy-paste them into the traversal loop. And if they reject the hit, then we just continue finding new intersections to test against. And at the end, where we don't have any new intersections anymore, we call either the closest hit or the miss shaders, basically. So there's a few reasons why we didn't separately compile any hit and intersection shaders. The most important reason is that ray traversal has lots of life states. So if you have an any hit shader that rejects some hit, you need to return to the shader at exactly the same point where you left off. And that requires saving lots of variables, and that can get expensive really quick. Also, you call lots of ray tracing shaders in the process of the ray traversal, because you have lots of intersections to process. So this higher overhead of each shader call gets multiplied by just doing much more shader calls to any hit and intersection shaders. So in the end, it was just always net negative on performance. So for implementing indirect jumps, we have the problem that each wavefront that has 32 or more shader invocations can actually only execute one shader at once. So we need to select one of the shaders from each invocation to determine which one to jump to next, and then just mask off all of the invocations that didn't actually want to call that specific shader. The problem with that is that in some cases, you might have some scenario where you have a shader call graph like this, where you diverge at a closest hit and a miss shader, and then reconverge at the ray generation shader. So both invocations that I show here, that will call one will call the closest hit shader, one will call the miss shader, but they're both called the same ray generation shader again. So if you just do the most naive approach of reading the first possible, the first valid shader pointer, you'll have an execution of something like this, where you start at the ray generation shader, of course, jump to the traversal shader, and then diverge at the closest hit and miss shaders. But when you actually execute the next step, then the second invocation will still be stuck at the mist shader, but since the first invocation wants to go to the regeneration shader now, we will first jump to the regeneration shader, where the first invocation will become invalid. Then we'll jump to the mist shader back, and after that we will execute the same regeneration shader again with the second invocation active only. So we can actually do better than that, where we select the shader based on its type, where we prefer, for example, closest hit and mist shaders over traversal shaders and regeneration shaders. And usually if you implement these indirect jumps for shader calls, you don't actually know the type of the shader, you just have some address and you don't know what type of shader there is. But we can actually circumvent that by exploiting the fact that on AMD, instruction always needs to be aligned to 4 bytes, so the least 2 significant bits of the instruction pointer are always 0. And there we can pack some shader type information in, and that's where we get the info on which shader to execute from. So if we prefer the closest hit and mist shaders first before executing any regeneration shader, the same loop would look like this. We go to the first traversal shader, go to closest hit and mist shaders, and diverge there. But instead of directly going to the regeneration shader, we execute the mist shader first, and then execute the regeneration shader with both invocations active. So I'm having not much time left, so I'll just go over the ray tracing status now really quickly. We've made lots of progress in compatibility. Like we had these games that worked at XDC 2022, and everything else was basically a gamble. It most likely didn't work, so probably don't even try. But nowadays we have pretty much everything that's out there working. So if you just run a random ray tracing app with Redvi, the chances are really high that it works. We have some hangs in The Witcher 3 and Cyberpunk 2077 currently, but that's pretty much all we know of. Of course, if you know of anything else that hangs on Redvi, please report an issue and we'll try to look into it. But usually the expectation is that it works. We've also made some great progress in performance. We've gone in this ray tracing reflection sample. We've went from around 1300 FPS to around 1600 FPS. Of course, we have still some optimizations to do before we actually match the AMD proprietary driver here, which currently reaches around 2000 FPS. But with that, let's look at actually what we actually want to do next for ray tracing. And the most important and obvious bullet point is to make the remaining games work. And the next step is to make them work actually fast. And for that, we have a few ideas. We have like lots of flexibility with the indirect jump shader calls, so we could explore some more sophisticated techniques for these shader calls, like shader execution reordering. But on the other hand, we could also look into expanding the monolithic path, which of course has much less shader call overhead, and making that work with pipeline libraries instead. Also, of course, on the roadmap is taking advantage of the RDNA 3 features I skipped over because Redvi doesn't actually use them yet. And on the acceleration structure side, we could either build higher quality BVHs, so we have to execute less traversal iterations, which of course makes the overall thing faster. And the other thing we could look at is acceleration structure updates, where Vulkan has some ways to modify already built acceleration structures without the hassle of having to do all the thing with rebuilding it again. So you just kind of change some small positions about inside the acceleration structure, and that's it. You usually don't have that much time spent in the building there, but Redvi actually doesn't implement this update path, so we just always rebuild from scratch, which could be optimized to also update, which would likely reduce the time spent building acceleration structures even more. And of course, lastly, we have tons of micro optimizations everywhere across the stack that we could do to make Redvi ray tracing much more than just the world's slowest ray tracer. And that pretty much wraps it up. So thank you for listening. I hope you enjoyed, and I'll be happy to hear any questions. No hands? That obvious?
What kind of work is there left to do for RDNA 3?
So it's basically just implementing the instructions that requires lots of refactoring in the ray traversal loop, where all of the instructions are currently aimed at. Like you have all of the shader instructions pretty much aimed at accelerating ray traversal. So lots of refactoring in that ray traversal shader that we have would be required to make use of these instructions instead of doing what we currently do, which is emulate the corresponding functionality in software. So it's basically just refactoring and then plopping the instruction in.
When you go from binary trees to these BVH4 trees, do you just collapse levels? Is there some cleverness to it?
So basically, the thing with BVHs is you don't actually always have 2 children or 4 children. Like, some of the children can be invalid, and the one non-trivial optimization we do instead of just collapsing is if we have another child that is invalid, we pull up more children from the other side so that the BVH in total gets flatter, and that means less traversal iterations.
So you're rebalancing the tree as well. Cool.
Okay, I think if there are no questions from Matrix or anything, then I suppose thank you for listening.
I have 3 more minutes.
be together, baby, as long as skies are blue. You act so innocent now, but you lied so soon. When I met you in the summer.
It's the time to start. I need a cue. Start? Okay. Hello, everyone. My name is Lucas Fryzek. I'm a new hire at Igalia. I started at the beginning of this year. I'm not new to graphics development, but I am new to the open source community and contributing. And so when I started, my colleagues had recommended that getting Freedreno to run on Android would probably be an interesting project to start with, to get familiar with Mesa and to start contributing stuff upstream. So in this talk, I'm going to cover a few things. All of them related to Freedreno, all of them related to Android. I'm going to talk a little bit about the state of the drivers with the Adreno GPUs and why this is important when you're trying to run something on Android. A little bit about why you might want to do this, how you actually build Mesa to run on Android, driver changes that are necessary to run on Android, and then some areas of needed improvement for Android support in Mesa. But to start off, in anything like this, it's important to show your work. So when I started my development, a lot of it looked like this, where you have broken rendering. That line in the middle of the screen is not my problem. That's a broken device, so I do apologize for that. It's not a problem I caused. But all the broken rendering behind that, that is a problem that I did cause with synchronization, things not working, the stuff being displayed before the GPU has actually finished rendering it. But in the end, it looked like this, where stuff actually looks like what you want it to look like. The capabilities actually report the driver as being Freedreno, and many applications running without any fault at all. So to start with the state of drivers for Adreno and Qualcomm GPUs, there is a tale of two drivers here. There are two kernel mode drivers that give you access to Adreno GPUs. One of them is a little bit nicer. It's the MSM driver. It's your friendly neighborhood upstream driver that is a lot easier to target, plays really nicely with Mesa. And then there is the less friendly KGSL driver, which is the driver that Qualcomm supports on Android, and it's what their proprietary user space supports. And so the work that I ended up doing was trying to get Freedreno actually to work with KGSL, because that's what you end up using when you run Android on a Qualcomm device. Now, there are some other things that are nice about using KGSL. One of them is that support for every SoC for Qualcomm is not upstreamed. So if you do have a use case where you're using Android, it can be a lot of work to try to merge upstream code into a downstream branch. And another interesting benefit I learned about as I was working on the project was that it provides the ability to run both Qualcomm's proprietary driver and Freedreno on the same hardware, in like a CH root, or just switching which driver is being loaded at runtime. And this was a pretty interesting thing, and I got a lot of, attention on my work, because apparently Panfrost already supports this, and people like to run CH roots on their Android devices to use hardware installation in a Linux desktop environment on Android. So some notes about the work I did. It wasn't entirely from scratch. Turnip already has very good support for the KGSL kernel mode driver. So a lot of the work that I did was actually based on the Turnip developers. So any Turnip developers watching this talk, thank you very much. You made my life a lot easier. And another nice thing about Freedreno is that the interface to access the kernel mode driver has already been pretty heavily abstracted. There is a interface in the source Freedreno DRM folder that provides a convenient API to accessing a kernel mode driver. In what is upstreamed right now, it currently splits support for MSM and the virtual I/O driver. And it's what I use to get all my work started for a different kernel driver backend. Now, all the work I did was on a Pixel 4a device. This was convenient because it has an Adreno 618 GPU, which is already supported by Freedreno. So I didn't have to worry about driver bugs at the same time I was trying to get this device working. I was using both two versions of the Android NDK, version 25 and 13. And later in the presentation, I'll talk a little bit about why there's two different NDK versions that ended up being used. And the other convenient thing about using a Pixel device is Google has this handy tool for Android where they have a bunch of ROMs available and a tool to flash them to your device. And this is very important because when you're messing with the system partition on an Android device, you need a user debug ROM that actually lets you unlock the file system because Android can be very locked down. So in my case, since I'm using a Pixel device, I can just go use this nice tool from Google, go find a user debug ROM for ASOP, download it on my device, and not worry about building a ROM myself. If you're trying to support this on a non-Google device, I think there would be a lot more work trying to get the user debug ROM set up, which would include building Android yourself. Now, that's getting started. What about building Mesa on Android? Well, it's actually a lot easier than you think. It's probably the easiest part of this project altogether. If you're targeting the Android NDK, it gives you a normal toolchain that you can just target with Meson cross files. And in fact, the Turnip developers have nicely written an Android guide for building Turnip on Android that you can conveniently use to build the same work that I did for building Freedreno. And like cross-compiling to any other target, there's some Meson configurations that you have to set for what platform you want. There's Android-specific ones for what SDK version you're targeting. So in my case, all the work I did was targeting SDK version 15 or 25, sorry. So I had to put that in there. There's Android stubs that you have to build just to deal with libraries that you don't necessarily have access to at build time. And of course, what drivers you want to target. In my case, Freedreno, and Freedreno also has this additional argument for kernel backends you want to build. So you, for the work here, want to target the KGSL kernel mode driver. Now that's great. We built something, but this isn't friendly Linux land. How do you actually deploy what you did on the device? You can't just set up an install folder, LD preload your install folder, and set whatever environment variables Mesa wants for loading the right driver. It's not that simple. You have to do a little bit more work and figure out what the heck Android is doing under the scenes. The Turnip developers have kindly wrote in that tutorial how to actually do things for Vulkan, and for doing things for OpenGL is very similar on Android. And for Vulkan, there's files in the vendor lib64, so a system partition for where the driver files are. In order to access those files so that you can write to them, you need to unlock the system partition, which is not that hard. As long as you have the user debug ROM, you can just run some ADB commands, and then you have read-write access to the system partition. And to actually find out what libraries Android is loading, thankfully Android is in fact open source, and we can see what's going on there. And you can just go into the EGL loader source code within Android and actually look at what libraries it loads, and finds out that it loads libraries from the vendor lib64 EGL folder, and it loads these libraries based on a vendor name. So you have to add a vendor name to what Mesa builds so that it can actually load the driver that you're trying to work with. So in my case, it's the Adreno one, so I had to add the EGL Adreno and the GLES 1 Adreno, and those are both used for the EGL implementation and OpenGL ES1 implementation respectively. The GLES v2 does not have the vendor name appended to it, and it provides the implementation for GLES 2 and beyond. Now, if you go and you replace that library, those libraries, and you go and you try to run something, you'll quickly find that it's still using the old driver. You run the GL Info app on Android, you'll see that Qualcomm's driver is still loaded, and you start scratching your head and going like, okay, what's going on here? And then this is another case where I'm happy that Android is open source and there is some documentation on this thing. And you'll find out that Android preloads the OpenGL driver that it uses at initialization, which is, I guess, good for performance on the system, for doing things like the system UI rendering and for applications, but it's not nice when you are trying to iterate on development and you don't want to have to restart your device every single time you make a driver change. So thankfully, there's a way to disable this preloading feature, and it's actually documented publicly within Android's documentation. There's this disable GL preload property in Android that you can override and set to true, so that anytime an application starts up on Android that's going to use OpenGL, it will reload the driver or the library. Now, the other thing about the setup with the kernel mode drivers is that Freedreno also expects some environment variables to be set, and on Android, you don't really have environment variables. They have their own system called properties, and thankfully, Mesa developers who have already thought this through and have added an abstraction to the environment variable system so that if you're running on Android, it will conveniently use props like environment variables with the added note that any underscore in a property name gets replaced with a period, and if the prop doesn't have Mesa in front of it, it will add Mesa in front of it so that they're all in the Mesa namespace. But doing that, we can now set all the environment variables we need to allow the device to, or the driver to load properly and start running. Now let's talk about testing. So with everything that I just talked about right now, if you want to go and open an Android app like an APK, it will go and it will load the driver and use it. You can open things like the GL Info app, and then, it's going to report all the capabilities that Freedreno reports. It's going to report the name that Freedreno reports, and that's great and all, but those aren't usually what graphics driver developers use for testing most of the time. A big part of our life is CTS, and thankfully CTS can be built as a APK so that you can run it on Android and actually see that your OpenGL implementation is conformant. But in my case, what I was doing is comparing my CTS results on Android against CTS results on Linux to make sure I haven't broken anything in the process. But this is not the most convenient developer environment. CTS is not quick when you're running through the entire test suite. I know probably a lot of you like to run things in parallel with DEQP runner. So I think you can imagine anytime you want to run CTS, having to sit through the whole thing is not desirable. So something that I did learn is that you can actually run command line applications on Android. The developers who worked on Freedreno reverse engineering very early on in the process set up this nice reverse engineering tools repo where they set up some application infrastructure that allows you to build OpenGL applications that you can launch from an ADB shell. And if you're not familiar with an ADB shell, that's basically just like Bash on your Android phone. You connect it to your computer, you type in ADB shell, and then it gives you a shell that you can start running commands on your Android device. So this is great. You can start building OpenGL applications. They have a nice framework put together, so you can look at that and figure out, okay, if I want to run an OpenGL application, I can do this. The big caveat on all of this is it's using EGL P buffers, and if you're not familiar with P buffers, they're off-screen surfaces. So you can run stuff, but it's not going to be shown on the screen. But in the case of testing, we're not usually looking at the results. It's a lot of just comparing results. So this is really nice when you're trying to rapidly iterate for development. Some caveats about this repo. So it has build scripts already set up, but everything in it targets NDK version 13. And there's a specific reason it targets NDK version 13, and that's because after that version, Google stopped shipping a lot of stuff in the NDK. And one very useful thing for us is that Google used to ship debugging tools with NDK 13, including GDB server, which is very useful when you're running applications in this environment, because if you have some kind of bug, it's nice to actually debug it, and you can't do that with the normal Android debugger within Android Studio. So in this case, you can launch your application, you can move the GDB server application from the NDK to the device and then use it to launch your applications that you built as more normal Linux applications, and then run them from the ADB shell. And then you can connect it to it from your computer, get a source code view, set breakpoints, do everything that you love to do with GDB. But we can even take it further. Although the stock CTS, when you try to build on an Android platform, only lets you target like an APK build, we can modify the CTS Android platform to build more like the Linux one, where it's a command line app, and then you can, again, copy that to your device, and then you can run it from this nice ADB shell environment. And in fact, if you keep repeating what I'm doing here, there's Cargo NDK, which is a implementation of Cargo targeting Android devices. That lets you build basically anything in the Cargo repos for Android, which includes DQP runner, which is great because now I can run tests and they will finish before the end of the day. So the source code changes to get this all working were only 900 lines of code. It was not that complicated. The majority of the changes were in the KGSL backend folder that I created in source Freedreno DRM. But there were also significant changes in this nice file called Platform Android in the EGL implementation. I'll start just with my changes on the KGSL backend. This was responsible for doing things like buffer object allocation and mapping, querying properties from the kernel mode driver, submitting command queues to the hardware, and handling synchronization. The majority of this code came from Turnip. Like I mentioned very early, Turnip already has support for this, so a lot of it I didn't have to worry about too much. I just had to translate it to the Freedreno backend interface. So it was a lot of copy pasting, and throughout the process, there was some code that could be moved to be common between Turnip and Freedreno. But not all of that has been done in the work I've been doing. So there's, again, always stuff you can do to clean up the code base and make it look nicer and work nicer and reduce copy paste. Some interesting quirks about the KGSL backend that caused me a few issues. There's no reference counting on buffer objects that are created within the KGSL kernel mode driver. So if you try to free a buffer that's currently being used by the GPU in a normal DRM driver, it will get freed at a later point once there's no references to it anymore. KGSL, as soon as you free it, it's done. And the first implementation where I got things running, I ran into interesting problems where I would MMU fault quite frequently because memory would be freed right in the middle of the GPU drawing it, and it was not fun, but it was fairly easy to figure out what was going on there. Another thing that caused issues was the KGSL kernel mode driver. In the interface to pass commands to it, it has a offset parameter that is completely ignored, and the GPU address is the only thing that's inspected, so you have to make sure that you include the offset in the address that you actually pass when you're telling KGSL the command object that you want it to run. There were some necessary backend changes that the Freedreno interface that I mentioned before didn't actually accommodate that were necessary in order to make it more general to different kernel mode drivers. The big thing was the way that frame buffers are allocated in Android are very different, and they need to be mapped in a different way. I'll talk about it a bit later, but they come from a different memory allocator, which is a lot of fun to deal with, called Grillo, and they need to be mapped differently than buffer objects that you allocate from the KGSL directly. So in the Freedreno backend, I needed to add support for a per backend implementation of mapping and importing DMA buffs to handle this unique KGSL behavior. Now, those were nice changes. They were easy to make for the most part. The platform Android changes were not as nice in EGL. This was a bit of a mess to deal with, and I'm going to talk a little bit about some of the not nice stuff about working on this project and some of the big problem areas that still exist within there today. So on Android, you have this nice graphics allocator called Grillo, which is used to allocate what it sounds like graphics memory. In our case, all the frame buffers for Android apps and for system UI and stuff like that are allocated in Grillo and then passed to us, the driver, and then we do our rendering to them. An interesting thing about Grillo is that it's implementation specific, but another thing about it is because Turnip runs on Android, they already have code to interface with it, so I wasn't starting from scratch again. But you go and you look at Turnip's code, and it looks like this. I don't know how obvious it is here, but if you look right there on the second line, that's not what I would call an API. You're just looking at an array of ints, and it's not documented what they're doing. There's some magic numbers there about handle data, like what exactly does that mean? And then you quickly find out that there's no externally accessible API to access internal data on per device implementations of Grillo. So it's not really meant to be general. And that code that I just showed from Turnip, the way that they figured that out is they looked at the Grillo source code for Qualcomm, they figured out where the data is in the structures, and just hacked it and made it work. And it works. You can draw the surfaces. It's not pretty, but it works, and it may or may not break in a future update. Just trying to get things working, I implemented the same interface for platform Android, but this quickly becomes quite unmaintainable. I would think if the more non-DRM compliant kernel mode drivers got support added in Mesa, because like I mentioned, there's no kind of general API to access this in this current implementation. The code that exists right now in platform Android can handle DRM drivers that are running on Android. So some devices already work well if you build an upstream kernel with and you use a recent version of Mesa. But in my case, where I'm trying to use the KGSL kernel mode driver, that option doesn't exist to me. I have to use the Qualcomm specific version of Grillo. There is, in fact, a newer API that is supported in Android, and it's under this file called platform_android_mapper.cpp, and there is a externally accessible API to interface with the allocator that I think would allow us to do everything that we want to do. But a big issue with it is that, as far as I understand, it cannot be used with the Android NDK, which is the main setup right now for building Mesa to run on Android, both in, from what I know, Turnip and my work in Freedreno. The big issue between them is this is provided by the Android system, and something Android does to kind of differentiate things because of I'm not an Android expert, so I don't know the specifics here, but anything that's built in the system that uses C++ and it's like using the standard library, it puts it in its own special namespace. And then when you try to build NDK apps, so stuff that's running as like user applications on Android, they put all the standard library in its own namespace. So if you try to access any of these functions, you'll find out that you can't actually access them due to namespace problems. The other issue that I found out is that you can actually use these functions if you build Mesa in tree with Android, like building, for example, ASOP. But it's my understanding that this setup of building Mesa in tree with like ASOP is likely to be deprecated. This is currently the alternative way to build Mesa without the NDK and get access to that namespace. So like I said before, I'm not an Android expert, so I'm not sure how useful this is, but if we had access to this from a convenient way to build, I think that would solve a lot of the problems with having a per driver implementation of the Gralec backend. So I'm going to talk a little bit about bugs I encountered. So a big caveat to all this work, none of it is upstreamed. I ran into some problems that weren't really related to the Android support, but were more Freedreno bugs that prevented it from working on Android in its entirety. The main one was an issue with services allocated by Gralec, and the fact that they don't necessarily respect GPU limitations. And so in my case on the GPU in the Pixel 4a, the blitting engine, when it reads pixel data to copy it, it does it in 16:4 chunks. And if the frame buffer that you're trying to write to or read from if it's not aligned to 16 on the width or 4 on the height, you will read outside the bounds of that memory and you will trigger a fault, which is what ended up happening for me. Whenever something was rendering towards the bottom of the display, it would trigger an IOMMU fault, and a lot of the times that would stop the GPU from working or stall or cause flickering. So in my opinion, this is kind of the biggest issue from actually making my work worth upstreaming. As it stands right now, if you try to use it, the Android UI will frequently cause this problem I'm talking about and start flickering. Most applications you run will work fine, just by an incredible fluke where on the Pixel 4a device, the screen resolution is divisible by 16 on the width and divisible by 4 on the height. So if you have a full screen application, it's great. You're not going to run into this problem. Unfortunately, the Android UI is not running full screen, so it does run into this problem. So this led me to a different path where I started looking into reverse engineering a little bit, because the Qualcomm Blob driver gets the same services that we do and is somehow able to render to them without causing this issue. So they're doing something a little bit different on the copying. But again, this is where things got kind of stuck. So I'm just going to talk a little bit about the Freedreno reverse engineering tools, because the last thing I did in this work was getting them to work for debugging this use case. And if you're not familiar with them, Freedreno has a diverse set of tools for inspecting the GPU state, but they're pretty much all designed to run from the command line in a Linux environment. So if you're trying to debug an Android APK, they're not that helpful. So in my case, one of the key tools I wanted to use was one called librap, which is a library that allows you to trace the commands being submitted to the GPU. As it works with both the Freedreno and Qualcomm driver, so you can capture traces between what Freedreno is doing, what the proprietary driver is doing, and start comparing them and seeing where the differences are. Unfortunately, it uses the LD preload mechanism to override system functions for things like open, read, write, to ioctl, for example, to actually capture those functions and then write them out to a file that you can use for comparison later. And because of the way Android works, you can't just LD preload, launch your APK. It's not as nice in Linux as Linux in that regard. So how do you actually make this work with APKs? Well, the first thing is trying to figure out how you can override system functions. And there is actually a way on Android to set environment variables for applications that are like Android applications that are being launched. And there's this wrap property that you can use. And the Android launcher will use that to set environment variables when it itself launches processes. So you can go ahead and use the ADB shell to set this wrap dot and then app name for whatever the app that you're testing is property, and then override environment variables like LD preload to get it to preload the libwrap, and then use that to start dumping the GPU command stream. Now, one big issue I ran into with doing this on Android was I quickly found out that multiple threads would suddenly start accessing the KGSL file descriptor. And the libwrap library was not designed to handle this. And so you'd go and you'd capture a trace, and it would not make any sense because you'd have commands inserted in the middle with other ones that were not coherent at all. And so I had to do some work in making the libwrap library thread safe, and so that this problem wouldn't happen. You could actually read the traces and they would be coherent. And that work is in fact already upstream to the Freedreno reverse engineering tools repo. So a couple conclusions about this. If anyone is looking to get their driver in Mesa running on Android, a lot of the infrastructure is already there. Like I said, there's only 900 lines of code roughly required to get this working. If it's a proper DRM driver and you're able to run that on use that on an Android system, then there's a good chance it will likely already work. If you want to use a downstream kernel mode driver and Gralloc implementation, that's where things get a little bit more messy. But a lot of this is open source, so even though it's messy, you can go see what that library is doing to get the per device specific information that you need for memory allocations to handle the stuff that you need to handle. Development is a lot faster when you do work from ADB shell. When I started, I was trying to figure out how I can do this in a more efficient way, trying to set up scripts that would launch APKs and get the Android Studio debugger connected to things so I can inspect the state. And it just, maybe if you've been doing Android development for years, this would be easier and you'd be more used to it, but I have not. I'm used to the Linux command line, and I prefer an environment that looks like that. And so once you can set up an environment like that on Android, I found development to be a lot easier and make things much quicker for doing my work. The last big conclusion is one of the biggest problems I think in Mesa right now for Android support is the Windows system integration. Like I mentioned, it's pretty ugly for how it's handled right now for both Turnip and Freedreno. Hopefully there are Android experts around that can comment a little bit more in case I'm missing something obvious about how we can get device-specific information in a way that doesn't require ugly hacks. So, this is something I would like to see improved in my changes, but at the moment they work without that, but you just have to be okay with a little ugliness. That's everything I have for my presentation. If you have any questions, feel free to ask, and the obligatory We're Hiring page, if you're interested, you can apply at the link. Sorry, I can't hear you that well. Could you get the microphone?
It is not strictly a question, but just thanks for trying Freedreno on top of KGSL. So this is not a thing that we usually do, and thanks a lot for your experience. Okay, small question. So at some point, a few years ago, we had to also modify the. Okay, it doesn't fully work. we had to modify Skia to treat Freedreno in the same way as treats the KGSL. Did you have to modify Skia in any way or not?
No, but Skia would complain a lot because Freedreno doesn't support I think it's YCRCB textures. But so as far as I understand, and again, this was a lot of my first experience dealing with more Android system level stuff. A lot of the UI in Android is rendered using Skia, and when I had it running under Freedreno, it just worked. Everything rendered correctly with the exception of when the IOMMU fault would happen, and then it would cause stuttering and flashes in the display. But when those issues weren't happening, the Android UI looked identical to running on Qualcomm's proprietary driver. And as far as I understand, all of that's running on top of Skia.
I heard the rumor that Google is pushing for basically at least the kernel side open drivers. Do you know anything about that?
No, I don't. I'm sorry.
Just a curiosity question. Do you feel like Google is closing the development area of the Pixel ecosystem?
Closing how? Sorry.
For example, I'm used to use Termux, and several commands that I already don't remember do not function because they are not available at user level, only if the phone is rooted.
Okay. I'm not sure I fully understand the question. Like in this case, the development that I did, you could only do when the phone is rooted because you need access to the system partition to replace the libraries. But if you're, a device, if you're shipping devices, you have control of the image that goes on that device, and then you would just include the Freedreno driver in the system partition at that point, and you wouldn't have to root it. I mean, obviously the end user at that point can't change the driver, it can only be changed by system updates. But the Android operating system is pretty restrictive in what a user can do on the device. So a lot of hacking like this, you have to root the device to just get access to what you need.
Pixel devices are pretty good for getting a user debug image, and those you can always get root on. Other devices, you're at the whim of the vendor. It's not up to Google.
Yeah, so at the beginning here, I'll just go back a couple slides. So Google has this flash.android.com tool. As far as I know, it's supported on all the Pixel devices. You can find user debug ROMs for a bunch of different configurations. In my case, I just used ASOP, and this gives you root access. It's very straightforward, not complicated at all to root the device and actually have access to start doing development like this on an Android device.
So before all, thanks for your talk. I think it was really interesting, and I wanted to ask, how do you feel about the fact that maybe users are being locked down for using free and open source replacements? For example, let's say Freedreno, it's included in a build for some custom ROM. after all, safety net is rowing towards the opposite direction, and after all, end users, like for example, let's say Google Pay or some Google services that are not easily replaceable by open source alternatives because trust and cybersecurity and all that kind of stuff. How do you feel like we can row towards completely Google-less or not Google-less, but let's say like free and open source entire functionality, no restricted end user experience?
Okay, so it's an interesting question. I had to say that personally, I don't like the fact that if you run like a Google app list, like Google services list device, a lot of applications you can't use. I find that fairly annoying, especially because there are things that are usually stuff that they're not like silly games. Like it's your banking app that doesn't work, or it's like your insurance app that doesn't work. So, no, it's not very nice. My opinion on the matter is I think it kind of goes against the spirit of keeping things open to the user. Like me personally, my experience growing up as a developer was, Linux was very open. You could, if you want to see how something works, you can go look at the source code. If you want to start hacking on something, you can go do that. You can build it. And I feel that it restricts that, availability. I do like on the Pixel devices specifically that it's easy to set up a development environment where you can start accessing system stuff. And I think it gives you some of that, freedom again. But yeah, I think I'm not a security expert, so I can't comment on if it's really that much more dangerous for a user if they have, a rooted device to access their bank information. But from the experience of someone who used things like hacking on the system as a way to learn how to program, I think it's not great. Any other questions? All right. Thank you.
Are we ready? Hello and welcome. My name is Christopher Michael. I'm going to do a live demo here of the Wayfire OpenGL Wayland compositor running using Pixman, which I know it wasn't meant to do, but that's okay. By the way, this is actually running on the Pi. It's going through a video capture. But anyway, okay, so as some of us know, the latest bookworm Raspberry Pi OS was released last week, along with the announcement of the RPI 5 device. The RPI 4 and the RPI 5 will come by default running Wayfire using OpenGL. However, because it's Raspberry Pi OS, we want to have the same experience across all the devices. So we need this basically Wayfire OpenGL compositor to run on RPI 1 through 3 also, which obviously we can't do with OpenGL. Oh, come on, mouse. There we go. So the challenges that we face doing this. Wayfire itself is strictly written for OpenGL. There was no software rendering at all on that. From previous XDCs, you may remember that on the RPI 3 and below, we can run out of GPU memory when using OpenGL. So obviously, we can't render the desktop with GL. So the solution we come up with was to implement software rendering inside the Wayfire compositor. However, we did still want hardware-accelerated apps to work, such as GLX Gears, GLMark, things of that nature. So it proved to be a little bit of a challenge. This demo is going to run on the RPI 3, which was released in February 2016 with a quad-core Broadcom 1.2 gigahertz, a Giga RAM, and the GPU does not have any MMU. So what I wanted to show is that even though this is software rendering, we can still get hardware acceleration. I mean, there's the obligatory GLX gears going on. And that's not using LVM pipe, that's actually using the VC4 driver. We also have GL Mark II. Basically anything hardware accelerated will work. Where was... I was told I had to display Neverball. No, I've never played this game before, so bear with me. Whee! Okay, that was fun. Okay, I can see how this would be addictive. All right, let's get out of that. There we go. Okay. We also, I don't know if it's on. No, okay, it's not. Gears, the Wayland version running. So, it is hardware accelerated. It is a Wayland compositor. We did have some issues in doing all this, which, come on, mouse. There we go. A lot of the plugins in Wayfire are written strictly for OpenGL using various GL calls. So one of the issues that we had to do is go through all the plugins in Wayfire, which are quite a few, if you've ever looked, and basically modify the code so that we can run via software in cases where we could modify the code. There are places where we could not. We ended up having to implement a new Alt-Tab switcher, which we can show here. And actually, it might be better if I had another window open, huh? There we go. So, I mean, it's a fairly basic Alt-Tab switcher, but it does function quite well. They also have, what was it, these two. The alpha plugin that's in Wayfire does work in software. And then we were also able to do the zoom plugin. Might be going the wrong way on the mouse here. Let's see. Yeah, there we go. Which also does, work using software. It actually works quite well, thanks to Lucas. Thank you, Lucas. So to achieve some of this higher performance, we ended up having to do some kernel patches to use, non-coherent buffers. Are those getting upstreamed, those patches? Do you know? No idea yet? Okay. And we also make use of DMA buffs and modifiers to import the application surfaces. This is still a work in progress. There are still a couple issues to sort out and a few more plugins to get working properly. However, it is on its way to becoming fully functional. Oh, well, I've reached the end. That was a fast 10 minutes. So I guess now we'll have some time for some questions if you'd like, or if I could display a few more applications. I don't know what else to run, though. We did the GLX gears already. Yeah. Don't think we had any other apps we were going to display, did we? It was the gears, the geomark. Yeah, that was kind of it. So, any questions? Oh, I see a few hands. All right.
Hello?
There you go.
Okay, so these patches that you were talking about that are still not upstream, is it something specific to Raspberry Pi enablement, or you can run this in other hardware as well?
Currently, the kernel patches, I believe, were specific for the Pi. But you can run the software rendering in basically anything. It doesn't have to be a Pi. But those patches we have not upstreamed yet. We still have some wlroots patches to upstream also.
So you can run the software rendering with accelerated applications in other hardware as well?
Correct. You should be able to. Yeah, as long as the hardware supports it, absolutely.
Could you give, is that working? Yes. Could you give any background on why Wayfire has been chosen for the
I
compositor?
can't speak too much to that. It wasn't a decision that we made. That was a decision from RPI.
Okay. Is it something they've created or something, that another project?
No, Wayfire is an existing compositor. You can run it on any desktop right now. Yeah, it's not a separate project or anything. It's not something specific to RPI, no.
Yes, sorry, I'm going to go back to Eriko's question.
Sure.
So the patches you have for VC4 are to allocate non-coherent buffer, right?
Mm-hmm.
Because otherwise you would get CMA buffers, which
you'd end up running out of memory.
Yeah. Yeah.
Mm-hmm.
So on ARM and ARM64, I think you have a DMA buff heap that already allows you to allocate those kind of buffers from memory and then get a DMA buff handle.
Right.
Why wasn't it a solution for you?
What? Oh, what made the hardware acceleration work?
No, I mean, why didn't you use a DMA buff heap to allocate those non-coherent buffers?
That's a good question. Yeah, it's sort of, yeah. Go ahead, Lucas.
Yeah, well, we can discuss it later if you want.
Sure.
So one of the big problems with them is it's not us that are allocating the surfaces. It's things like Mesa that's allocating the surface, or it's X11, GLX, X Wayland, that stuff. So there's a lot of places where you'd have to modify it, where those things just use the DRM APIs directly. And so if you fix it if you change the way the DRM APIs work on VC4, then it fixes it for everything, as opposed to having to make this change in all these other places.
Okay, makes sense. Thanks.
Any other questions?
So you said the motivation for using software rendering was because you were running out of VRAM?
On the older devices, yes.
Yeah, so I'm just curious about like how much VRAM do the older devices actually have?
I guess that varies by model. I mean, the B plus probably has more than the regular B.
Yeah, because like a 720p frame buffer would be like 3 megabytes or whatever, so it must be really small.
On the RPI devices, yeah, it's a bit limited. I don't have exact numbers in front of me. But,
yeah.
Okay.
I can answer that a little more.
Okay.
Yeah, so the Pi 1 through 3 don't specifically have VRAM. The issue is that there's no MMU behind the GPU, and so you're relying on Linux's CMA allocator, which works sometimes, and then sometimes just says no. You don't have a specific number of, you can allocate this much memory. It's fragmented, other things get pinned into it. You get no mem out of it all of the time. And so this software rendering plan is the workaround for, we can't put every buffer into CMA because the kernel just says no.
Yeah, exactly. Thank you for that. Any other questions? Okay, well, thank you for your time.
So, this is the end of the first day. I would like you to remember. I would like to remember you about the social event this afternoon. We have it's 6:15, the guided tour through the city center of the city. There are going to be 3 guides. They are going to give the explanations in English, so don't worry about that. Partners, friends, family, relatives, whatever, they are invited as well. So I highly recommend you use, if it is the first time you are in this city, I recommend you to take it. Now the weather is helping. If you ask me 1 hour before, it was raining as hell. But so yeah, remember 6:15 in the front of the venue, downstairs, we will start the guided tours. Thank you.